Shall we start, Jagabandhu?
Yes, sir.
Jagabandhu, we have to take attendance that we are doing, no?
Yes, sir.
ठीक. Okay. So, good afternoon and welcome to the fourth day in this GAN course on cognitive speech processing. In this session, I will give a brief overview of this neural networks and deep learning area. As all of us know, not only speech, in many areas, the deep learning has helped in developing technologies whose performance is much superior compared to earlier technologies whatever we have. So in that way, the aim of this talk will be just to give you links on how all this happened. I have organized my talk in the following way, introducing the field of whole artificial intelligence and associated subfields. Then I will talk about the distinctions between neural networks and deep neural networks and what caused the breakthrough in deep learning. Then some important deep learning models like briefly about convolutional networks, sequence models like recurrent neural network, LSTM, time neural networks, adversarial neural network. Then, of course, I may not cover much on restricted Boltzmann transformers. Some applications I will mention. For these terminologies, you might be aware if you are working in the field. These terminologies we use broadly or interchangeably in many contexts, like artificial intelligence, pattern recognition, machine learning, and deep learning. Even though we use them interchangeably, it is good to get the distinction in terms of under what context these terminologies have been evolved. When it comes to the artificial intelligence, the naming to this broad field came that identifying the fact that whatever commonsensical things humans do, they are treated as naturally intelligent tasks. Now, if you are trying to mimic them and enable the computers to perform these tasks, perform these intelligent tasks, all those technologies or techniques they are termed as artificial intelligence, that field. Some examples like, any speech mode of communication is a natural intelligent task by humans. Recognizing other people looking into their face is also a natural intelligent task. So I want to equivalently enable capabilities to the computers to perform such things. So since computing machine is a digital electron circuit, which does not have a cognitive system, so naturally, we are just mimicking the ability. So accordingly, they are termed as artificial intelligence approaches. Then came in that broader umbrella of artificial intelligence, this pattern recognition came, which essentially said you carefully look into how humans interact with the external world. They try to do a pattern way of processing. So accordingly, um, they wanted to bring this pattern concept onto the computing machines, and that field was called as pattern recognition. Then came after that what we call machine learning. Of course, we use this pattern recognition, machine learning interchangeably very often. However, the pattern recognition field essentially refers to all the approaches which are meant for recognizing the patterns. And whereas machine learning, there also the goal is pattern recognition only. However, the way they discover the underlying pattern in the given set of features is by an implicit approach rather than an explicit approach. Okay, whereas in the pattern recognition, we have explicit approaches for recognizing the patterns. Of course, we can also make use of the machine learning methods for pattern recognition. But if the discovery of the patterns present in the given set of features happens without being explicitly programmed about what pattern to look for, that comes under this paradigm of machine learning. So, in that way, if I go for a pattern recognition tools, it is a superset. There may be some tools which don't go by this discovery. The fixed way of discovering the patterns are there. Hardwired approaches plus this machine learning approaches. Whereas the other way is not true. The machine learning method you can use either for discovery of the pattern or discovering something else also. Okay, so but by an implicit way. So that means to say pattern recognition always includes the machine learning for discovery. It can do something pattern recognition by other template matching approaches also without implicitly discovering the pattern. So that is the distinction. That's finer distinction is there, but otherwise no. Now though we use interchangeably. That distinction we may have to keep. But it has so happened that most of the applications for machine learning is only pattern recognition. That is why we use these two terminologies interchangeably. This part I emphasized earlier. When I go to deep learning, not only discovery of the patterns, we can also discover the underlying nonlinear representations or the features first from the raw data, then use these nonlinear representation features for discovering the pattern. That is why it is called as deep learning. So, in that way, if you take deep learning, machine learning, pattern recognition, they're all at a bigger role. They are meant for performing intelligent tasks on computing machines. So accordingly, they come under that broader field of artificial intelligence. So these terminologies we need to have some clarity. Of course, a lot of material is available in the public domain. You can look into it. This also, I don't know, I mentioned in the previous lectures, but worth it once again. So if I go for traditional machine learning approach, what we were doing earlier, we had a very extensive feature engineering block where we all made our livelihoods in the initial days of our teaching and research. That as signal processing community, we spent a lot of time in processing the raw data and coming up with a feature representation. And a lot of emphasis was given, especially before this machine learning came, when conventional pattern recognition was there. Most important preference was given to a feature extraction stage. It was a belief that if your features are good, your pattern recognition system performance will be good. Rest is only okay. That is just a model to learn the patterns or comparison the pattern. So as a result of that, not much. But in the machine learning, okay, people say that feature engineering is required, but somebody else will do. I will only take the data points. But interchangeably using machine learning and pattern recognition, if I see from the raw input, I have this feature engineering, signal processing engineer who discovers the features and use these features in the traditional machine learning model to find out the classification boundaries or model the distribution of the classes and then use it for a different task, say classification task. Whereas when I go to deep learning, all these three things, feature engineering, features, traditional that classification, everything is clubbed into one model. You give raw data, initial layers of the deep learning model will learn the representation by nonlinear processing, and these nonlinear representations are further combined at later layers to do the pattern classification task. Okay. Then coming to the if you look by the structure and feel, it almost any deep learning model also looks like a neural network only. In fact, it is maybe treated as an advanced topic in the neural network theory, because all these deep learning models that we are studying now, they came as advanced topics earlier. So, but, however, there is because the era of neural network was also there 80s and 90s. but their performance was not even at par with any of the other non-neural network-based machine learning or pattern recognition tools. So in that way, we need to understand the distinction between neural networks and deep learning. As I mentioned here, the concept of deep learning is first originated from this neural network only. Of course, one of the important architectures, whether you take neural network or deep learning, is the feed-forward neural network. If I take feed-forward neural network, the workhorse algorithm for feed-forward neural network is the backpropagation learning algorithm. In fact, when the backpropagation learning algorithm was not there, really the feed-forward neural network field was stuck for more than a decade, not having a proper learning algorithm to train even the simple neural networks. When the backpropagation learning algorithm came, it gave a procedure for training the shallow feed-forward network. However, what they found was when you increase the number of hidden layers beyond 3 or beyond 3, they found that the backpropagation learning algorithm is not able to do well. That means to say it is unable to backpropagate the errors from the output layer to the more hidden layers that are getting created. And also, another phenomenon they observed that if you have insufficient data, because at that time insufficient data is an issue, it was leading to overfitting and difficulty in training of the deep networks if I want to train a deep network. So these two limitations led, even though this convolutional network, recurrent network, these literatures are there during the era of neural networks itself, we were unable to train them well because of the several issues. That is why the interest in the neural networks field went down. And of course, there are subgroups. They continue to work along the direction of how to make or train this different neural network. In that, one breakthrough came, just like backpropagation learning algorithm came. Another breakthrough came in the neural networks field by Professor Jeffrey Hinton's group from University of Toronto. They, for the first time, demonstrated that it is indeed possible to train a deep belief network using a greedy layer-wise pre-training. I'll explain about greedy layer. That came in 2006. Of course, rest is history. Many other groups reproduced the result, not only for deep belief networks, but other type of deep networks also. They demonstrated that these deep neural networks outperform any of those machine learning technologies that we were using earlier. So the learning strategies and models have undergone changes and which enabled training the very deep architecture. So that is why now we are talking about several tens of layers in the deep network, and we are comfortably training them and getting a very good performance. Of course, if you just if you look into the root cause, the genesis for machine learning is in pattern recognition. Similarly, the genesis for deep learning is in the neural network. Okay. So, like this pattern recognition is the basis for machine learning, neural network is the basis for deep learning. So, as I mentioned earlier, deep learning enables both learning features as well as modeling information in a better manner. Generally, we get confused that now deep learning model has more number of layers. That's why we call it as a deep learning layer. Of course, that is one reason. But the another equally important reason is starting from the raw data, we can go on in a layered fashion, go on discovering the representations and then culminating them in the form of patterns. That hierarchical way of processing where each hidden layer, we can assume it to learn certain concept or certain representation. So accordingly, in a hierarchical manner, these concepts are further combined to the next layer to get a next bigger concept. So that is why that is called as a deep learning. Yes, please.
ഞാൻ കുറച്ച് ബിസിയാണ് ഒരു മീറ്റിംഗിലാണ് കേട്ടോ.
Pardon me, Govind. Okay. So I just want to bring the point that deep learning models, the nomenclature is not just because of the number of layers in the deep learning model. but also because of the hierarchical way in which they learn the concepts. Okay. If you see, how do I relate deep learning, machine learning, AI? This deep learning can be treated as a specialized field in the machine learning. In that way, it's a subset of machine learning. Then machine learning in turn is a subset of field of artificial intelligence. This figure also gives you a picture. If I see the machine learning, you have first you extract the features by some signal processing method. When you have a raw input by any, these symbols are just to indicate that you are doing investigation to get the feature representation. Then you use this feature representation as the data points for the input layer of the machine learning model. Do the classification output here. Similarly, when I go for deep learning model, we don't have this manual or semi-automatic investigation what we are doing in the machine learning case, where directly you connect the raw input to the several hidden layers, which they themselves will discover the representations. Okay, so that is the distinction between machine learning or deep learning. This is another picture which shows, we go for the neural network of earlier, shallow neural network. Input layer, we used to apply the extracted features, and then hidden layers will essentially discover the patterns and store the pattern information in the weights, and classification output comes. Whereas now, if I come for the deep learning, you can see I can apply the raw face image itself as input, raw data. That is nothing but the pixel values. Then the first hidden layer may be assumed to extract the or represent the edges present in the given image. So the concept here in what is being modeled in the first hidden layer is the edges. Similarly, when I go to the next second hidden layer, it will try to merge several edges to get a combination of edges. That is there in the second hidden layer. Similarly, when I go to the third hidden layer, we will have further combine those edges to get higher level of concept. That is, now a portion of the face can be identified. Finally, when I go for a combination of features, then you get the final facial output, distinct facial output are there from one for each of the output node. Okay. So you can see this pictorially, the input is the pixel values. From there, granularity increases. First hidden layer will extract certain. It cannot handle directly extract the face images because from the raw representation, it cannot directly jump into the pattern information. So that is where first it will just only feasible thing is edges it will recognize. Then the combination of edges, which may reveal you some small pattern-like information that is there. For example, here it is a nose, there is an eye here. Similarly, then it goes to the bigger area of the facial image. Then their combinations to get the face. So this is what is being, that is how we call it as deep learning. Pixel values, next level, and so on. That is why it is called as the deep learning. So this I already showed. This is how the relation between neural networks, artificial intelligence comes into picture. Deep learning is a part of neural network we can treat. It's an advanced topic. Then the neural network is in turn part of the machine learning and then the artificial. Now, the issue, we were unable to train a deep neural network at that point of time. I told no, backpropagation was unable to propagate the errors properly, which is essentially was termed by a very well-known name, what is called vanishing or exploding gradient problem. That means to say, when I'm doing the backpropagation learning algorithm, I am backpropagating the errors from the output layer to the hidden layer inside, towards the input layer. Okay. So now what happens is, when I'm backpropagating the error, it so happens after traversing through few hidden layers, the error that is getting propagated becomes either vanishingly small or a very large value, which has no relation to the actual error gradient that is there. And if it becomes infinitesimally small, that is called as a vanishing gradient. If it becomes very large, we call it as exploding gradient. So now, when we are backpropagating, it was becoming either exponentially small, becoming vanishing gradient, or exponentially large, becoming exploding gradient. In both these cases, the weight adjustment has no value because you are not really adjusting the weights of that hidden layer by using the actual gradient or error. So that is where the weights are not getting tuned to the actual input data and discovering the patterns. So as a result of that, the training will saturate at some high error level. That, and we say, since the training error is not decreasing beyond certain, the difference between successive epochs is less than certain threshold, we prematurely converge to a poor solution or a local minima. This was the problem we were facing when we were trying to increase the number of hidden layers at that point of time when we were doing this neural networks. Then people started know how do I handle this. That is where this deep learning community started looking into. Then they felt, suppose if I consider the feed forward neural network, which has say 10 layers, and if you directly stack all these 10 layers together and train at once by using backpropagation, seem to be going nowhere because of the vanishing or exploding gradient problem. What they felt was, is there any way I can initialize the weights? Now, unless specified, it goes by random initialization. But in place of random initialization, can I come up with some alternative ways of initializing the weights of all these layers such that they have prior exposure to the actual input-output data that we are at hand to train the deep learning model. So people started exploring different weight initialization mechanisms. And also, in the deep feedforward network, if you see, the sigmoidal weight function we use as an activation function. Since that sigmoidal activation function quickly saturates beyond certain limit, so they felt, no, this is also another reason why the error is not getting backpropagated. Can I replace that activation function with some alternative activation function? So these are the two things which became highly successful to make enable the deep learning model train. Coming to the alternative weight initialization mechanisms, what they did was they, in an unsupervised pre-training manner, they first, using the input-output data, there's no output here, unsupervised, only input data, they tried to capture the information about the nature of the distribution and use them as that knowledge as weight initialization purpose. Similarly, in the supervised way, layer-wise training was done, and or unsupervised way also we can do layer-wise pre-training, and variations on the gradient descent. They come up with different gradient descent strategies such that I can reduce the effect of vanishing or exploding gradient. That is one direction of work. The other direction was, instead of using the sigmoidal function, can I have alternative activation function, what is called rectified linear unit activation function? That became very highly successful in terms of sigmoidal function like tangent hyperbolic. The beauty of this ReLU function is it acts like a linear function for certain range. For example, from beyond 0, null negative input, it will make 0. And beyond 0, any positive value will be linearly varying. So since it is a linear portion is there, so naturally the error backpropagated will have significant value. Accordingly, we can minimize the effect of the vanishing or exploding gradient. Okay, but it's still a nonlinear function because I have half of the portion I have rectified. That's why it's called a rectified linear unit by the nonlinear function, forcing negative inputs to 0. So in that way, this became a very successful. So both these strategies helped in training the deep learning models. Okay, I think when I go for this greedy layer-wise training, let me go directly there. This I mentioned in the beginning, when upper layers of the deep network are supposed to represent more abstract concepts that explain the input observation nature, whereas the lower layers extract low-level features. This example I gave. Upper level layers towards the output layer abstract means distinct face images, whereas lower layer features means edges from the input raw data. Okay, what is greedy layer-wise training means? You do the pre-training of one layer at a time in a greedy way. Greedy means each layer is pre-trained to model its input, ignoring the effect of the higher layers. That means to say, suppose if there are 10 layers in the feed-forward network, suppose I want to train the first hidden layer. Train the first hidden layer means I want to adjust the weights of the first hidden layer as in the concept of pre-training. When I'm training greedy way, the input to the first hidden layer is the raw data. Raw data is the input to the first hidden layer, and the first hidden layer is, the purpose of first hidden layer is it has to capture some hidden variables which are not directly obvious in this raw data. Discovering that hidden layers, hidden variables, each of these neurons in the first hidden layer are treated as one of those hidden variables. And then the raw data is given. Say if there are some 10 nodes are there in the first hidden layer, each of those 10 represent distinct hidden variables. And the goal is, how do I do the training in such a way that from that hidden layers learned in the hidden variables learned in the hidden layer can be used to reconstruct back the raw data. In that portion, the greedy layer-wise training is done to maximize the information modeling by the first hidden layer in terms of hidden variables from the raw data. Whenever I want, I should be able to reconstruct back the raw data. So keeping that greedy layer-wise training is done. Okay, that means to say, when I'm taking the first hidden layer, it has to do its job best without worrying about what the later hidden layers will do. It is not that I will extract certain things when I become a part of the 10 hidden layer neural network. On the other hand, when I take it separately as a one hidden layer network, I capture something else. That is what is the greedy layer-wise training phenomenon. Each layer is pre-trained to model its input, ignoring the effect of the higher layers. I don't bother about what higher layers effect will be there on this data, but I just want to take a maximum benefit of given data and model some of its hidden variables. Okay, so in that way, now input layer and the first hidden layer are taken together in a restricted Boltzmann concept as a part of deep belief network, and undirected graph will be there as a connection between the input layer and the first hidden layer. Using that, learning happens such that maximum information is captured for bidirectional reconstruction. From the given raw data, I should be able to construct the hidden variables. Similarly, from the hidden layers, we can reconstruct back the raw data. Okay, so that is what is done. So then using learning at each, then when I want to train the second hidden layer, I take the first hidden layer, I'll pass the raw data through the first hidden layer, and whatever the output comes from the first hidden layer, they are used as input to the second hidden layer. And now the goal of or objective of greedy layer-wise training for the second hidden layer is, from this input, that is the output to the first hidden layer, again you get the hidden variables which are present in this first layer output. So that is how we train. So once in that way, greedy way, we train, layer-wise training is done. 10 layers are trained as separate modules. Then you go and plug them, stack them together in one 10-layer network. Then you do the final tuning. When I do final tuning, backpropagation, it has not avoided the vanishing or exploding gradient problem. Only the first few, because ultimately the abstract concept of the pattern is in the top layers. Those errors are adjusted, but anyway, these earlier layers are all been pre-trained. As a result of that, they used to give consistently better performance. So this is the breakthrough result that came in 2006, and that gave us a direction for the. Okay. For example, if I unsupervised way, if I train layer-wise greedy training unsupervised way, then I just don't keep any output layer, just take a pair of layers and try to go by the restricted Boltzmann machine concept. On the other hand, if I go for layer-wise supervised training, train each hidden layer as the hidden layer of a one hidden layer supervision network. There is input layer, there is hidden layer, and then there is an output layer. So with the help of that, you adjust the weights of the hidden layer. Okay, then throw away the hidden output layer and use the trained hidden layer as a pre-training initialization for the next hidden layer. Okay. So repeat this process as input to the output of previously trained layer. Final fine-tuning is done for adjust. Okay. Just to summarize, the greedy layer-wise training which came was either unsupervised or supervised way. If in the given deep neural network, if I have n layers, you take out one layer at a time, train each layer separately in a greedy manner, and then plug them back into stack them this hidden layer in sequence to get the deep feed format. Okay, that is about that. So of course there are several deep learning models. That is a deep feed forward neural network was trained like that. Then when I came to the one of the important deep learning models that are there, what we call convolutional networks, which you might have heard, people use extensively in the literature. The motivation for that was, especially when we are training the spatial data, image-like structures. Earlier in the deep feed-forward neural network or multi-layer perceptrons, you convert the two-dimensional data into one large dimension vector and use them as one-dimensional vector for training the deep feed-forward neural network. Then the people who proposed this convolutional network, then they felt, no, the information related to the fact that the original data generated is a spatial information is there in the spatial content. Can I give the two-dimensional data as input to the training of the neural network? Those are called as convolutional neural network. Okay, and also they also told, suppose I give raw pixel as input to the in the spatial domain, I give it as input to the neural network, and the output is coming, say, facial recognition of face of a person. The learning is in a hierarchy of concepts. Starting from the raw pixel values, you should finally arrive at the individual face information. That is also they identified, because again here the working of the motivation from the structure and functioning of the human brain came into picture. In the human brain, from the evoked potential that is entering into the neural pathways, how finally the combination of the message happens is the neural pathway bioelectric potential goes through deep structures, several layered manner. Finally, it gets into that concept. Okay, that is how they told, okay, I can have several convolution layers to mimic this hierarchy of concept. Okay, so in that hierarchy concept, as I explained earlier, you learn the simple concept first and then use those simple concepts to get the next abstract level concept. Okay. Now, naturally, the people told, no, instead of one dimension, you're using two-dimension data. Naturally, it will be much more computationally intensive compared to one-dimensional processing when you're doing two-dimensional processing. But what they found was, as I explained in the cognitive system, this one, the representation in the spatial domain is very sparse in nature. So when it is sparse, you don't really, once you do some smoothing or something, only very few parameters will have some appreciable value. Those only are taken to the next. So in that way, the number of computations also significantly reduces. Okay. Of course, there are some neuroscientific basis for justifying the two-dimensional processing. For example, just like auditory cortex, we have visual cortex. When I take primary visual cortex, which is responsible for visual scene processing. So what they found was the two-dimensional image that gets created on the retina will get transformed as a two-dimensional image to the primary visual cortex. Okay, that recreation happens. And also they felt that the primary visual cortex is arranged in a spatial map and as a two-dimensional structure, mirroring the structure of the image on the film. So accordingly, the two-dimensional way of processing will essentially mimic the primary visual cortex functionality. So as a result of that, and then since only a subset of neurons in the primary visual cortex is activated for a specific type of image, we can go by the sparse processing. So accordingly, you can employ what they call nonlinear processing by the detector units. Original thing is convolution for the first level to no derive some sort of feature for the next level. Okay, then reduce the dimensionality. You can do the pooling. So that is what they came up with this convolutional network. We have three important concepts. One is the convolution. Essentially, the convolution, like any other signal processing, meant for getting the output response, means in this case, essentially to compute the feature representations, next level smoothed version to go further. Okay, that is the convolution. Then nonlinear processing by the detector units. Finally, smoothing by the pooling. So, first thing is the convolution, then the strategy of detection followed by pooling is repeatedly applied for many layers to mimic the deep structures aspect. Okay, and accordingly, it finally reached that stable abstract concept. Okay, so that's the cognitive systems aspect that were exploited in the structure and functioning of convolutional network was we had the um, spatial knowledge, so that I can put this two-dimensional data. Then the sparse interaction, because only few neurons in the spatial domain will fire to specific pattern image that is given as input. And with the help of pooling, you need to store only few parameters for the further processing. So that is how they exploited and reduced the number of computations. And rest is history, because convolutional network became highly successful. Now, one of the most important convolutional network, new deep neural networks for a feature extraction are the convolutional neural networks. This is one direction. That is about the feature extraction part. The second important direction was what we call sequence modeling, where the class specific or discrimination information is in the sequential order, the temporal order. Okay. For example, if I consider many examples, I'll give in the next slide. When I go for this convolutional network, unless specified, we are trying to capture the distribution or discrimination among different classes by using feature extraction followed by some fully connected layer or something. Whereas there are some cases, some time series data are so, like speech, audio, or any such natural language processing, sequential of text words. There, the discrimination or class specific information is in the sequential order or the temporal order, position or time stamp. Okay. Thus, anytime when we want to derive the pattern information, we exploit that sequence knowledge. Okay, so that is where that is not accounted either when I go for multi-layer perceptron or feed-forward neural network or convolutional neural network. That is where they have to come up with the different neural network models which can exploit this sequential knowledge from the given data for modeling that information. Okay. So, for example, few cases if I consider, suppose if I go for speech recognition, the input speech signal X is a speech signal, and the output Y is the sequence of recognized words. Okay. So, if you listen to the speech signal when they are played, it comes from t equal to 0, some t equal to 2 seconds you play. By listening to that sequence of speech samples, you are able to make out the spoken message. Similarly, you can make out the message in the recognized words by reading the entire sequence of words. That is that speech recognition. Similarly, you can extend it to, if I go for music processing also, sequence of frames of video, and then the output is action depicted. The whatever, no, you will feel that. So that way, you can go through the other things also. Most of the cases, the pattern information is in the sequence. So that is why we need other type of neural networks which can exploit this sequence modeling knowledge. Of course, before this neural network, we have a well-known stochastic modeling approach called hidden Markov models. In the hidden Markov models also, we exploit this sequential knowledge. However, what is shown in the hidden Markov models is the sequence knowledge that can capture is relatively smaller length compared to what we are talking about in the deep neural network models. For example, we have recurrent neural networks and its variants like gated recurrent neural network, long short-term memory, or bidirectional long short-term memory. All these things can indeed capture longer temporal sequence knowledge. Similarly, another sequence knowledge capturing neural network is what is called time-delay neural network, which essentially meant for capturing the shorter sequence knowledge like hidden Markov models. Okay, so that is what is. Since one of the first neural networks for sequence modeling was recurrent neural network, it is important to just to understand the key idea for moving forward from multi-layer perceptron to recurrent neural network. One thing, what it makes distinct in case of recurrent neural network is, if I go for multi-layer perceptron, every link will have a unique weight parameter, which will not be shared with any other link in the whole multi-layer perceptron network. Whereas when I come for recurrent neural network, the same set of parameters are shared across different hidden layers. Like at different instants, I use the same set of weight parameters. Okay, the sharing parameters across different hidden layers, as opposed to independent weights in the case of MLP, is one of the fundamental distinction between multi-layer perceptron and recurrent neural network. One thing we may get into our mind that now why do we want to share the parameters, and mainly because when I come for time series data, you have a sequence of variable lengths. Suppose assume that in one case the number of data points in the sequence are 1000. For the same example, next time it can be 990 or it can be 1100. Then how do I deal with variable length sequence? By sharing parameters like this, it does not matter. Same parameters I'm getting updated as more data points are coming in the sequence. So that is where the concept of sharing weights across the different nodes came into picture. So this sharing is important when the further, if the sharing becomes important when the specific piece of information can occur at multiple positions within the sequence. It can come in any position. For example, we call a well-known named entity recognition in natural language processing. That is nothing but in a given text sentence, spotting the name wherever it comes. That it can position, it can come in the beginning or in the middle or in the end. Okay. But if I'm saying named entity recognition task, I should be ready to spot that names in whichever position is coming. So if I am sharing the parameters and the training procedure is such that to spot only the name, position does not matter. So that is where the concept of the sequence modeling came into picture. And also, as I mentioned, it relates to optimized structure. Okay, some sort of what is that happens is, since the same set of parameters are applied and again at the different instance of time or different instance of positions, we call the happening again and again, which is called as a recurrence. Some sort of recurrence happening in the network. That's why the name called as recurrent neural networks. Okay. Suppose if I consider any recurrent RNNs, they will operate on a sequence of vectors. The sequence or order matters much. That is, training data you have 1 to tau. Okay. So it operates on that mini batches of such sequence with the different tau can vary from one example to the other example. The tau value can vary, but since we are sharing the parameters across different systems, it does not matter varying. But fundamental assumption is yes, I will have variable length sequence. Okay. For example, let us say we are given the input x1 and the activation value A0 to first node in the RNN, and it predicts the first input output at that timestamp y1, y hat 1, where the actual output is yn. So by computing the error between y of 1 and y cap 1, I can adjust the weight parameters connecting A0 x1 and the intermediate output to the y cap 1. So now when I go for computing take input as x2 and the activation value from the previous time is passed on as another input to the second timestamp prediction of the output. So accordingly, I am using the previous sequence knowledge to predict the output at timestamp 2 equal to. That is that exploiting the sequence knowledge. Then the same weight parameters which are there here will be used here also for updating. So that is why this matrix of WAX, WEA, WYA, you don't worry about the notations, but these are the different time weight parameters in the basic element of recurrent network, which will be shared across input, hidden, and the output connections. Of course, another thing that is important in the case of recurrent network, we call backpropagation through time. Now, what happens? This concept is not there when I go for conventional networks or deep feedforward networks, because there is only time. That time knowledge is not there. Sequence knowledge is not there. It is essentially capturing either the discrimination among the classes or modeling the distribution of the classes. Time is not there. So the backpropagation is only through that layers which are at a given instant of time. That means to say time or position is unimportant. We have randomized it as a feature vector and trained the system. Whereas, since we are ordering them in time, here we got this concept of backpropagation through time. And this backpropagation through time, in turn, became a much bigger problem in the recurrent neural networks for training compared to the problem that we are facing for conventional backpropagation, which is independent of time. Okay, and that resulted in again this vanishing gradient problem in RNN, which essentially the weight update that we are trying to do, starting from the last time node going back, only few nodes you can adjust the weight, it will become meaningful, but other nodes it is not much. So that is where people thought about how to overcome this vanishing gradient problem due to backpropagation through time that is occurring in recurrent network and its variants. So that is where they came up with the different variants. One is called gated recurrent neural network, which essentially you will have additional gating mechanism. In the gating mechanism, what we do is whether to preserve the previous knowledge of the generated so far, or I can use the current knowledge which is generated. So in that way, this, because when I'm doing the sequential approach for pattern recognition, when I am taking a decision at a particular point of time, I may need the knowledge at some previous instant of time. And that knowledge is indirectly adjusted through the weight parameters. Since we are going through this problem of backpropagation through time, specifically, I can remember that previous output with the help of a gating mechanism. Whenever, suppose, out of the n outputs, I think fifth output is important to derive knowledge at some 12th output, and the remaining 6, 7, 8 up to 11 are not important. I board the output at the fifth output and preserve them till we go to the 12th output. At the 12th output, I use this knowledge to generate the output. That is what is this. For example, this equation is important. At this point of time, the memory cell value is the updated gate value at this instant of time or from the previous time instant. So this previous time instant can go back in time using the same equation. With the help of that, I can now preserve the information for later use. That's why it's called as gated recurrence. I can only put a gate, like a logical gate, to either preserve the current value as the memory cell value or the previous instant of time as the memory cell value. Of course, its variants came fully gated recurrent. One more gate they put it, essentially to have additional parameters while preserving the information. this further, of course, this LSTM came earlier than gated recurrent node. Here also we have one more gate. One is called update gate, forget gate, and output gate. So with the help of them, we can better control the flow of information from one part of the sequence to the other part of the sequence. So of course, so far when I go for recurrent neural network or gated recurrent network or long-term short-term memory, unless specified, we are thinking only in the forward direction. But there are some sequential pattern recognition tasks where at any given instant of time, the output at that point not only dependent on what has occurred in the past, it is also dependent on what will occur in the future. So as a result of that, I should have the sequence knowledge from forward direction, also backward direction. So that is where I can compute both forward direction and backward direction activation values and use them together to compute the output at y cap t. So that's what called as signal flow is in both directions. That's called bidirectional recurrent neural networks. Of course, you have deeper version of these neural networks by adding what I explained is only for the one layer. You can have more layers repeating the same operation. Okay. So then came this, of course, it was there parallelly. If I go for time-driven network, if I want to model the shorter temporal context, where when I go for recurrent network and its variations, I can think about the temporal modeling across spoken words, made across seconds or several hundreds of milliseconds. Separated events can be modeled in the sequence. Whereas when I come for time-delayed network, I model the temporal context information across only few milliseconds. Okay, that is what is the time-delayed neural network. The name time delay comes into picture because if I have a given set of data points, their time-delayed versions are also considered, and together that knowledge is put into training the weights of the network. Okay, weighted summation of delayed inputs and passing through the output function. Okay, that is why I call it time delay neural network. So this also gave a very good performance, especially in the shorter temporal context. Okay, so that is another sequence modeling technique. Of course, you can compare this recurrent neural network and time delay network. When I come for recurrent neural network, as I told, it is for modeling the longer temporal context, whereas TDNN is for modeling the shorter temporal context. Okay, and then recently we have last few years we also have one more concept, what is called attention modeling. There the sequence knowledge is one. Suppose if I want to decide on the output at that particular instant of time, I use the sequence knowledge occurring at another position or time instant and use that. But here in the attention, suppose I want to derive certain output. To derive that output, out of all the multiple inputs given, which one is most important for me? I can give more weight for that. Similarly, the next best one, I can give second weight for that. So that, for example, given the training data, with the help of the training data, I will try to derive such knowledge. That we call it as attention vector or context vector. Okay. So with the help of that, I should a priori know during testing, for example, for this output node, I have to pay attention for this is input context modules. So that is where the concept of attention vector came, which the sequence knowledge also we are paying that type of information to some extent. However, this is more explicit. We can avoid the recurrence because people found that when I'm doing recurrent neural network or its variation, it takes a lot of time because I cannot parallelize things. It has to go in a sequence knowledge. Whereas in the attention modeling, I can bring out this attention vector in a parallel manner. So that is where it reduces the computational complexity by parallelizing things. Essentially, without attention modeling, y is equal to f of x, whereas now I will have the y output will also depend on both input data as well as the context vector, which is derived during the training process. Okay, and the neural network architecture which exploited this attention concept was called as transformer network. Now the transformer network, almost has replaced the recurrent neural network and its variations because of parallel way of computing the output, as well as you are specifically targeting and trying to learn the attention things, and it exploits two types of attention mechanisms. One is called the basic self-attention mechanism, and a combination of several such self-attention mechanisms called as multi-head attention. With the help of that, they are training the a transformer network, which is supposed to be much superior compared to recurrent neural network or its variants. Some of the brief applications, if I see, I told this convolutional network, it will have three subparts in that. Any convolution layer, if you take, three subparts will be there. One is the convolution layer, which essentially extract, by filtering it, extracts some features. Then I do the, I can reduce the data rate by pooling. You can do the nonlinear processing by passing through a nonlinear activation function. How many convolution layers you will use? It depends on how many level of granularity you need. So each of the convolution layer can be treated as extracting the feature vectors. Finally, when I want to do classification output, you can take the last convolution layer output, pass it through a fully connected layer, and pass it through softmax to get the output. Similarly, I can use the autoencoder network as feature extractors. This bottleneck layer will act as a reducer dimensional vector for the input. So that is the way we can do. Similarly, I can use the variational autoencoder for, instead of getting the reduced dimensional vector, which I can treat it as hidden variable or latent space, I can actually capture the distribution of this latent space or the feature vectors. Once I have the distribution, I can not only reconstruct the feature vectors represented by the distribution, but also the what we call, you can generate more data points. That is why this variational autoencoder will act as the data generator. Okay, and another successful model is the generative adversarial network, which essentially will have a generator and discriminator. The generator network will not directly learn or does not have contact with the original data distribution. It learns through discriminator network. Discriminator network will only give yes or no relations. Based on that, it will try to learn starting from a random data point distribution. Finally, it arrives at the actual data distribution. So that is what is generative adversarial network. The discriminator forms the adversarial flow. Classification network, I told, no, if I want to do classification, I use the fully connected layer. So let me summarize. So I briefly highlighted what is the breakthrough in deep learning that happened, briefly mentioned about convolutional network, sequential models, generative adversarial network. Restricted Boltzmann was only in terms of training greedy layer-wise unsupervised training, transformers, and some applications I mentioned. If you see, many of the deep learning models and concepts, they're inspired by the organization and functioning of human brain. But it was more psychological studies they have made, psychologically how the brain functions for certain activity, for instance, sequence modeling, how it will do. Based on that, how can I come up with a parallel and distributed processing model for the sequential model? Similarly, of course, the deep learning is very useful in handling many applications. So what I wanted to summarize is, many of the cognitive system functionalities studied either as a function of neuroscience or as a psychological studies have been exploited to come up with different deep neural network architectures. So that in that way, this cognitive processing also paves way for advancement in the field of the deep learning model. Okay. I'll stop here. Thank you for listening. If you have any questions or clarifications, we'll be happy to.
Sir, when it comes to selection of particular type of the network, because there are so many varieties of the networks available.
Correct.
So what should be our logic thought process? How should we go ahead?
Yeah, no, that's a very, very important question. For example, if I have assume that my pattern recognition task is exploiting sequential knowledge, then it makes sense only to use sequential models, whether you use RNN or gated recurrent networks or LSTM or transformer network. It depends on that. Suppose for that sequential knowledge task, you go and use convolutional network, it has no meaning. Similarly, if you have the distribution, the actual discrimination among the classes is among the distribution, then we have to go for, any distribution capturing models, including multi-layer perceptron or generative adversarial network. Any of those things we can use. Further, suppose if I go for sequential models itself, there are a battery of sequential models. Which one I want to use? Again, it depends on, of course, many researchers have put forward the information in the literature. May not be for, not only for speech, other areas also. With that knowledge, depending on the functionality we have, we can see which of those sequential model will suit me better. For example, if I want to model only the shorter temporal context, which is across tens of milliseconds, then it makes sense to use time neural network rather than recurrent neural network. So in that way, the domain knowledge is important. Based on that, we can select the most suitable deep learning architecture.
All right. Thank you. Thank you very much, sir.
Thank you. Any other questions? Okay, there are no more questions. Thank you very much. Let me stop here. I'll request Professor Ruffiner to take over. Professor Ruffiner.
Okay, hello, how are you?
Fine, Professor Ruffiner. How are you?
Very well.
Please.
I will share my screen.
Yes.
I think that yesterday we took two of the lectures. And now we have the half part of the yesterday lecture because I have more time in order to finish it now.
Correct.
So I think perhaps we have to cut the recording when I finished this lecture, and then again, I don't know.
Jagabandhu?
Yes, sir, we will do that.
Yeah, we will take care of that first.
Thank you. So I will share the screen now.
Yeah, it is visible, Professor.
Okay, thank you. Well, now we will continue with the lecture 7 from yesterday, speech-related via signals. So in the first part, we review the principal type of speech-related signals that you can measure in different parts of the body, also with different type of sensors. So I think that we stay here in what is called electromagnetic articulography. So I will go on from this point. Electromagnetic articulography is a technique where you use magnetic field sensors that they are placed on the main articulators, and a magnetic field is produced by coils with another equipment. So in this way, this type of sensors can record magnetic activity in the change in the position, especially of the different part of the human articulators. It can be used to determine the complete vocal tract configuration with the precise tracking of all the sensors in 2D or 3D space. So there are some commercially available devices. And here is one manufacturer. And the idea is to register the different trajectories of each of the main articulators. Here, if you then want, you can see a video and an animation where each point in each place of the, for example, the mouse and the neck and different parts, and even the tongue, they are moving while you are producing some type of speech sound. So it's really an invasive procedure because you have to put these sensors even inside the mouse. It is not suitable for everyday use. Here you have a picture with the equipment and the person that she is here producing some type of speech. And with all these electrodes, they are really magnetic field detectors. Try to produce the different sounds and then record all the variations there. Another type of techniques that are useful in order to get information from the speech production process are all kinds of techniques that can produce images or animation or even videos. Practically every available imaging technologies or techniques were applied to analyze the speech production process. The most common are normal videos. You can, for example, record with a camera, a video camera, all the process from outside or even inside with endoscopy and something like that. You can also use ultrasound videos. Well, this is a very, very useful technique also, because you can see how the different internal parts of the body moves when you produce the different sounds. Also RX rays, tomography, and MRI. Here, for example, you have a place that is like an atlas, where you have different images and animations of the different parts of the process of different phonation sounds and the corresponding articulatory movements, for example. Well, here in this picture, you see an ultrasound recording system. Here at the right picture, you can see the different parts of the human production system. Here is the root of the tongue, the surface of the tongue, and the tip of the tongue, and also other meaningful parts they are there, and you can see how all this stuff moves around time when you produce the different phonemes, for example. So this type of technology was even used for some application like lip reading or even silent speech recognition, because you don't need to do any sound, and you can register especially all articulatory movements and articulatory transitions. So here, this is an image taken for the paper, where they propose especially a silent speech recognition system using only this type of videos or animations taken from ultrasound images. Of course, this is in general not so practical, but in some applications, it could be useful also. So now all the other techniques are related with indirect measures of speech by using different sensors that the ones used for brain signals. So now we pay special attention which what happened with brain activity signals or brain activity related signals. Previous biological techniques or techniques for register biosignals are especially focused in extracting information from the speech production process. And the advantage with brain activity signals is that they can also be used in order to extract information from the speech perception process, because this type of this process is really mostly a brain internal process. Because the speech production system involves many organs of the body, so you can register with several sensors in the different points. But here in the for perception is all the perception is inside the brain. So the one of the possibilities is to use brain-related signals. Both processes, the production and perception, of course, are really interrelated in the brain. So we will see that it is very difficult to completely isolate, for example, activity that belongs to the production process from the activity that belongs to the perception process. In what follows, we will see the different techniques and equipment we have in order to register this type of signal. And also we try to show you some examples about how these type of techniques are applied in order to record specific features or characteristics of the production and perception of speech. So here in this picture, in the bottom, you can see the activation, for example, of the speech motor cortex in the left hemisphere in red here, and in the right hemisphere in red also, and the activation of the auditory cortex also here in blue in both hemispheres. So you can see that both activities can be quasi-simultaneous, so it is really difficult to isolate one from the other. Well, the first type of recording methods are the invasive methods or technologies. We talked a little about this type of recordings, like ECOG or IEEG. In this type of recordings, the electrodes are implanted in the surface of the brain, of the cortex. And so here you have really an optimum quality, because you can register local signals of thousands of neurons, but you have a very high spatial resolution. But you have a lot of disadvantages, like risk of infection and scarring. So because of the high temporal and also space resolution of this type of techniques, it has been extensively used for study different processes, in particular the process of producing or perceiving speech. So in particular, one of the advantages is that you can register high frequencies that are difficult to register using other equipment like EEG or EMG. Special interest is or are the gamma waves, that are the waves that with frequencies upper from 30 hertz. This type of waves are really involved in some of the functions associated with producing speech, for example, or even to perceive the speech. So here you have in this picture, you have in red the position of the different electrodes of the array. And in all the cases, to register this type of three-dimensional images, you use MRI. And then you can superimpose the position of the electrodes here. So it is raining here. Sorry for the noise. So in these pictures, you can see EcoG gamma envelope. It is the envelope for the gamma waves in these particular frequencies. And here you have in the green electrode, you can see this type of temporal evolution for this particular gamma band across the time. And superimposed there, you can see in gray, I don't know if you can see really because it's not very easy to see, but it's in the background. And you can see that there is a very important correlation between the envelope of gamma frequencies in green, in this electrode, and the corresponding speech envelope for this towards that is abolish all. And then you have something similar, but in another part of the brain, in blue. And again, here you have the corresponding envelope of the gamma frequencies for all the evolution of both worlds again. And also you have an important correlation between them. So this is an important finding that gamma waves are related with some meaningful characteristics of the speech perceived or even produced. This is from a work from 2015. So here we have another picture.
Excuse me, sir.
Yes.
Sir, in this previous slide, does that mean that those gamma ray waves, they are produced at only specific locations? They are not produced throughout the brain?
Sorry, can you repeat?
Those gamma signals, are they produced only through specific positions in the brain, or they are
Yes.
available?
That's right.
Okay.
Yes. As in other types of brain registering techniques, you have a lot of electrodes here in different positions on the brain. Each position is associated with some area of the brain that is responsible to some function there. For example, here, this is associated to the motor cortex, and in particular to movements of the lips or something like that. And here, this is associated more with the auditory cortex in this way. But both of them are really very, very high correlation with the speech envelope because of different reasons. Okay?
Okay, sir. Thank you.
In what follows, we will see this type of things in more detail in order to try to understand how all this process occurs in the brain and how we can decode from these signals all the speech-related activity. Okay.
Yeah. Okay, sir. Thank you.
Thank you. So in this other picture, You have another type of resistor from the same method, EcoG. So here in this picture, you have, again, a matrix of electrodes. I think that it is a little small, but here are marked two electrodes, X and Y here. And then in this other picture, you have the average evoked potentials and the high gamma event relay band power. That is specifically the version, the filtered version of the event relay potentials in the gamma band. That they are recorded from these two sides I show you here, these two electrodes in different parts of the brain. And what you can see here is the response to the syllables pa, ba, da. Pa, ba, da. In C and D, you can see respectively the average evoked potentials and the high gamma event related band power here. And in each rows, you have to respond to pa, ba, and da. And in the columns, the successive frame temporal line every 50 milliseconds. So these are different time windows over the same part of here of the brain cortex. For anatomical purposes, here you can see the different structures there. So as you can see in the picture, the activation changes from one part to the other during the stimulus presentation. And the activation is different for the different phonemes or the different syllables in this case. So in this way, you can see again that the gamma waves are very important in order to try to decode this type of processes for speech production or speech perception. Here in these electrodes are specifically put in the part of all the auditory cortex and what is called the Broca area, in order to know or try to decode all the signals related with the production or even some type of perception of speech. Well, that's for the invasive technologies. Invasive technologies are really very good for research, but not for everyday use. So another alternatives are the non-invasive technologies. We will review now the main technologies, like magnetoencephalography here. You can see here the equipment that is really big equipment and also very expensive. Then you have here functional magnetic resonance. That equipment also very expensive, but very big, not portable. And in the last row here, you have functional near-infrared spectrography or spectroscopy here, and electroencephalography that we talked really a lot in the last lectures. So I will try to describe the principal characteristics of every one of these techniques, and then see some examples of how this was applied to record with different type of characteristics from brain associated to speech activity. So magnetoencephalography registers brain activity by means of magnetic induction, measures the intracellular currents flowing through dendrites which produce magnetic fields. So these neurophysiological processes are really identical to those that produce EEG signals. but magnetic fields are less disturbed by the skull and scalp than the electric field. So that's an advantage, because with this type of techniques, you can really try to detect where are the dipoles that are responsible from the different potentials in the surface. A high spatio-temporal resolution can be achieved with this type of equipment, but they are, as I mentioned, they are too bulky and expensive for everyday use. So here in this picture, you have again a person that is doing the experiment. In this experiment, they try to record some of the signal during the speed perception. So in this graphic, you can see the position of the different sensors, EME sensors. You also have a cap here, similar like the one used in BCI. Sorry, like the one used in EEG. And in yellow, you can see the sensors that are near the principal part for responsible for the perception of speech in the left part of the brain. So here you have a tonotopic map where in each part of the head you find a particular wave that is associated to the auditory evoked magnetic field response because of the speech stimulus. And here you have the topographic distribution of the magnetic field over all the head by a bidimensional representation. In particular, this was the register of the N100 peak latency, that it is especially related with some type of perceptual characteristics. And here in this plot, you have the temporal evolution of all the sensors altogether. Well, in this other study, because as you can see, this is a very raw analysis of what happens with this type of recordings. But really, the idea with this type of technique is to try to infer the position of the dipoles, like in this other study. For reconstructing this type of brain activity inside the brain, you have to use inverse models. So you try to measure the different field potentials in the sensors, and then with this type of inverse modeling, you can localize with very, very accurate estimation the position of the different dipoles. For example, here you have in this picture, you have the auditory evoked response to a train of tone picks. Here is the stimulus, the different times, and here are the different registers from the left and side hemisphere at the different times here. This is the different waves, M50, M100, etc., of the different types of the evoked response. So from this, you can infer the positions of the different dipoles over the auditory cortex, because the auditory cortex is really folded. So some of the activity is really more depth than over the surface you can act directly or measure directly. So this type of techniques is very useful for this reason. Of course, there are many type of inverse models, and this can be also a difficult problem to solve. Another thing to mention is that here the only information that is related with this type of technique is the position of the dipoles. But all other here image is produced by MRI. So you have then to superimpose both images, and this is also a difficult task. So there are some techniques in order to get all this stuff together. So you can see really where that position are related with the anatomical structures of the brain. Okay? Well, another non-invasive technology is what it called functional magnetic resonance imaging, or fMRI. It detects changes in local cerebral blood volume, flow, and oxygenation levels during neural activation by means of electromagnetic fields. It really uses MRI scanners which apply electromagnetic fields in the order of 3 to 7 Tesla, and they have a very high spatial resolution, but low temporal resolution in the order of 1 or 2 seconds. Hemodynamic response introduces additional physiological delay in the order of 3 to 6 seconds also. And this type of technique is highly susceptible to head motion artifacts. So the person or the subject has to be really very quiet and trying not to move the head because of this reason. In this picture, we can see how this technique works. MRI is used to determine the anatomical structure as in other type of studies. Sometimes it's the same equipment that do both things simultaneously in different stages of the recording. So the MRI of this behavior of the brain. Generally, they use together. So you can get this type of image where in gray you have the anatomical structure, and in different colors you have how the brain modified their metabolic function during time. So this type of MRI images were recorded for speech production process. So here in this column, in A, you have the register of speech versus baseline. In general, in this type of studies, you register both conditions, baseline, that is, baseline condition is like the background noise, all other activities, not the speech. And then, or even speech can be there, but in general, the subject is quiet in baseline, trying to not do any task, any particular task. So this is like background noise. So then you register the same study, but for a speech condition. So then you have to subtract both studies in order to get what's the difference in activation from one state to the other. That is what we are seeing in this column. As you can see, different parts of the brain are activated during this speech process. We will in the later we will go on more on the details of what each of the parts of the brain are involved in which phase of the speech production or speech perception process. In this other column in the middle, you have the difference between voiced and whispered modes of speaking. So you can see the principal difference between both modalities. And then here, a different type of phonetical content for different type of phonemes. For example, phoneme with bilabial versus alveolar characteristics. So again, you have different type of properties that you can extract or information from this process. And here in the bottom, you also have the flat cerebellum representation, because not only the cortex is involved in the process of produce or even perceived speech, but also the cerebellum. The cerebellum has some important functions in the process, as you can see here, because this is also the difference between both baseline and speech. And you have a lot of the parts of the cerebellum activated during speech, as you can say, what you can see. And similar for other particular tasks. But here you see that for some characteristic of a speech, they are not present in the cerebellum, but some others are really very present there. Okay. Then in this other picture, you can see another study of MRI maps during speech perception. So here you can see how the place of articulation of the sounds you are, or phonemes you are hearing, affect the metabolic or the blood in the different parts of the brain. So here you have in green in this part. In B row, you have the manner of articulation, how the manner of articulation was represented in the different parts of the brain. You can see that this part is associated more with the motor cortex, and this with the auditory cortex here. The same from the other hemisphere. And in the last row here, you have voicing activity. So when you use or you hear voiced phonemes, then particular parts of the brain, they are activated. Okay. Well, another functional technique is what it called functional near-infrared spectroscopy. This is an optical spectroscopy method in order to characterize fluctuations in the cerebral metabolism during neural activity. In this case, the idea is that infrared light can penetrate the skull to a depth of about 1 to 3 centimeters. So this type of study is really limited to the outer cortical layer, not more depth than 2 or 3 centimeters. So vascular changes occur after some neural activity associated with one of these phenomena, and then you can register that changes with this type of technique. The spatial resolution of this technique is quite low, in the order of 1 centimeter or more. They are relatively low-cost equipment with high portability, similar to EEG, and acceptable temporal resolution also, something like 100 milliseconds per each sample. So in this picture here, you can see the different waves that you can register with this type of technique for each one of the lighting diodes that you have in the cap. It's a cap similar like the one in EEG, with lighting emitting the diodes or diodes for each of the positions. Here, this equipment has 98 sensors in all the head or channels. And here you can see, for example, 3 particular channels from 3 different subjects and the variation between them. This, of course, is related with the change in the hemoglobin profiles in each one of the subjects during some particular speech task. Here is during speech production. This is similar to the sensor that are used for oximeters that you put in your finger. So in this picture now, you can see the result of projecting or transforming this type of data into a three-dimensional representation. Again, this type of imaging grade is produced with MRI. And you use one type of triangulation-based linear interpolation in order to get this type of images here. In particular, this fMRI is show this task that is a silent picture naming task, an overt silent speech paradigm. Then you really imagine naming some picture. For example, in this task, you see a picture and then internally you have to give the name or pronounce the name of the picture you are seeing. So here, I think, this is the silent picture naming mask, and here in bottom row, you have voxel-wise analysis showing the activity, but with a different type of method in order to remove the global component. So you only retain the main characteristics of the task you are trying to measure there. Well, and in this point, we arrive again to electroencephalography, EEG. I have just talked a lot about this type of resistor. It measures the electric brain activity caused by the flow of electric currents, the electric potentials. Again, during synaptic excitation of the dendrites in the neurons. The signals are easily recorded in a non-invasive manner through different electrodes placed on the scalp. It provides a really poor quality signals because signals have to cross the scalp, the skull, and many other layers of tissue. And so also this type of resistor are severely affected by background noise inside the brain or externally over the scalp. Even some myographic origin noises are produce artifact in EEG. One of the problems with this type of techniques is that some currents produce potentials that cancel each other. So you have here a very, very difficult or difficult, very, very hard for the solution of the inverse problem. That's not happened with magnetic fields, as I already mentioned. So here it is really very difficult to know the particular spatial position of each one of the dipoles. But even though it is far by the most widespread recording modality. So in this other slide, we can see the EEG recording for the speech processing during working memory task. Working memory, the idea here is that you have to pronounce a particular sequence of numbers here, but you have to, in a particular part of the sequence of the number, you have to remember the previous two numbers, one of the previous two or of the previous number, and you have to repeat it. So that's the task that use also part of the memory, the working memory, in order to produce the sequence of words. So here in A, in this part, you have the temporal frequency response of the power changes between task at two electrodes. This electrode, AF zeta and O zeta. Here, yes, here is one of them, and here is the other. And then here you have the topographies for theta and alpha frequency bands. Here you have theta, and here you have alpha. And you can see how this type of memory depending producing speech related with different parts of the brain. For example, some of the here there is some activity in the frontal part of the brain. So in this other picture, we can see a representation of two of the main important characteristics of this type of techniques: spatial resolution in this axis and temporal resolution in this other axis. So here, with a really very high temporal resolution, you have principally the main invasive techniques like ECOG. And in the middle, you have EEG and EMG. And then with less resolution, NRIs or fMRI. Here is the same as NRIs and fMRIs are similar. One are the images and other are the functional part. So as you can see, EEG is really a compromise between spatial and a good compromise between spatial and temporal resolution. So in this picture, non-invasive methods are in blue and invasive methods are in red. Well, then to finish this lecture, we have a brief summary of how the different type of sensors and signals can be used in different type of applications of speech communication. For example, here you have the different speaking modes that we see at the beginning of the lecture: modal or normal speech, murmur speech, whisper speech, silent speech, and imagine speech. That's the column of this table. And then in the rows, you have applications that can restore or enhanced speech communication, therapy and training for speech, robust speech communication, and mute speech communication, and also which techniques can give some insights about speech communication. So you can see that EMG, PMI, and EcoG are really useful for whisper or silent speech. This is, of course, apart from the acoustic signal and the other related signal. And from look at from imagined speech or even inner speech, we will see the different in what follows. EcoG is one of the only techniques that appear in the works that these authors look for in the different papers. They look for different papers in the last years, and they construct this type of table. So if some technique is not here, if it's not here, it's not appear in the work, but it is not impossible to apply that technique to the problem. Okay. So here you can also use EEG and another technique, fMRI or something like that. Well, for therapy and training, you have also for model speech, most of them. For robust speech also. In many of these applications, the idea is to use a multimodal approach in order to use more of one signal in order to better recognize speech in hard environments. And then here you have mute speech communication. And well, you can see the details then in the work. And for insights or research, all the methods there were used. Okay. This is another summary from this review from Lee et al. 2021. And in this case, authors put all the techniques here, and then the different organs that are involved in the produce of a particular signal. So here you have the oral cavity, the muscles, and the brain principally. And inside the oral cavity, you have the tongue, the palate, the lip, the larynx, and between the muscles, principally in the face and the neck. And here you can see that with EMG is one of the most used techniques in the work this author review in his paper. So EMG was used to follow changes in larynx and face and neck, isolated or together. Of course, EEG, always for rain, that is really what we are expecting. And other techniques like EPG and tongue drive system, and multimodal speech capture system using some of multi-sensors or arrays for taking the signals. Okay. This is all for this lecture. I ask for questions.
Okay, will I stop the recording and restart it again?
Okay. Let me close here the doors.
Sir,
Yes.
sir, I have a query.
Yes.
Sir, actually I work in paralinguistics. With reference to the paralinguistic information, how this will be represented in the auditory cortex? I think most of your talk were based on the linguistic the speech, right? So paralinguistic information, is it directly we can observe in the auditory cortex, or it is a collective? There will be the information is spread across the brain.
When you say paralinguistic, you refer to semantic and all of that.
No, linguistic means related to the language, the sound units, vowels, all those things. So paralinguistic,
Okay.
what I meant was like expressions, emotions, etc.
Okay, okay. Well, if the emotion is expressed with speech, then you can see some cues in this type of representation also. But for emotions, if you try to record only the emotion, then you have the limbic system and the amygdala.
Oh.
There you have the principal activity for emotions, not here in the cortex.
Okay.
Okay.
Yeah. But what I was thinking was like some of the studies. People, when we speak, when we are actually under stress or other emotional states, our breathing pattern will change, respiration will change, etc. So some other physiological activities will be there.
Okay.
So yeah, so will there be any sort of mapping that can be done? For example, the work you are showing yesterday, you're doing some kind of mapping, right? Some auditory spectrograms that you are actually doing. The similar kind of mapping can be done, like with reference
Yes.
to the paralinguistic information. For example, a person is having some disability, cognitive disabilities, like Parkinson, or like neurodegenerative diseases like Parkinson's disease, or something like that. So if the doctor wants to analyze the speech patterns, whether a particular the to test the mood swings of the patient, something like that can be, some insights can be observed by that kind of mapping.
And surely, if you record during a speech production or a speech perception, you can try to follow some cues there.
Yeah.
But the emotion, it is there not only when you speak. Okay, so
Okay.
for for experiments that don't use speech, I think that this can be useless.
Oh,
You understand? But if you during the process the person is at least imagine speech, I think.
okay.
For example, you can instruct the subject in order to try to imagine its own voice, but angry.
Okay.
Then I think that you can get some of these characteristics, for example, in the auditory cortex.
Okay. So that
But
means
yes.
this paralinguistic information is not confined to auditory cortex of the brain, right?
At least not the most important components,
Oh,
because really, as we will see, all is mixed there. Or there is very difficult to isolate particular aspects of a task.
Okay.
Some tasks have one of the characteristics dominant, but really all the brain is involved in many of these complex tasks. Okay?
Okay. Thank you, sir.
Thank you. So now I will begin with the other lecture. a minute. Okay. Well, the idea for this lecture is that we can now talk about speech, but related with BCI. Together we revised the different aspects of speech, for instance, and BCI, but now we try to see both aspects together. So do you remember this slide? Yesterday we began with this slide about speech
Yes.
communication. We told that this is the most natural form of communication and all of that. You have a lot of information here. This is a person shouting to his phone. But now the idea is what happens is here I put a brain-computer interface. It is possible to use brain signals related to speech production for communication. That's one of the questions. Another question can be, how are the underlying brain processes that generated these signals? Another question we will try to answer is, which are the differences between traditional BCI paradigms and speech-related ones? Because really, speech-related are the newer or the newest paradigms. But this field has many other alternatives. So which is the difference between these new paradigms and the other ones? Another question we will try to arrive is, which are the advantages and the disadvantages of using this type of control signal for brain-computer interfaces? And also, are all the speaking modalities equally interesting or useful for this task? And if we have enough time, which are the difference between a speech-related BCI paradigms? Okay, so let's begin. Now we will review the brain processing for a speech production. In the last lecture, we reviewed the different techniques in order to recording the different signals from brain. But now the idea is to put the focus in the different process. How the brain processes speech and how the brain processes speech for production, especially, but also for perception. So you remember this picture that I showed you the first day? Here you have a positron emission tomography scans of the human brain activated during different tasks. As you can see here, in this task, the person has to see a particular word. In this case, the occipital visual region or area of the brain is activated. In the next picture, you can see what happens when you hear a word. Here you can see a very sharp activation of the auditory cortex, and here all the part that is responsible for audition. And then here you speak the same word, and the Broca area activate. And in this part, you are thinking on a particular word. And as you can see, many years of the brain, they are activated. This is a very basic analysis, because this is only a static picture of a very complex dynamical process. And this type also of image are really old one. The brain imaging methods advance a lot. So now we have a very interesting techniques in order to get some insight about how all this happen inside the brain. We will review the main models or functional models of the production and perception process. So here you have a classic oversimplistic model of language processing and speech production. This is the left hemisphere. Here you have, for example, the Broca area. The very first models only use two areas of the brain, the Broca area and the Wernicke area here. And then both of them are connected. So the Broca area is responsible, or was responsible in earlier models from speech production, and the Wernicke area is responsible for speech perception. But these are really very simplistic model. When the study is advanced, they propose more complex modeling of this process. So in this model, the idea is Broca area is responsible for message formulation by applying basic language rules like syntax or phonological rules. And then motor cortex coordinate the fine movements for a speech production, and that's all. That's the most simplistic version of the production model. Broca area makes the message formulation and then send it to the motor cortex to produce the movements and produce the speech. But really, Wernicke and other perception areas are also involved. You can see, in order to get an idea of what happened, you can think about how speech and language are developed. For example, when you are a child, we all simultaneously develop both abilities, the speech ability and also the perception and comprehension ability, all together. Because our parents told you, told us different words, and we try to extract the meaning and try to pronounce the same word, and by repetition and reinforcement, then we can develop both abilities simultaneously, production and perception. So really, I think that in this with this type of idea, you can exploit new models that can handle simultaneously both modalities of this complex process. I think that some years ago, I see a model that produces speeches. It's a speech synthesizer, but in the same process of learning how to pronounce or generate the sounds, also learn how to characterize the different sounds. And I think that last year some authors proposed a similar model. So this is an important and interesting thing to work in. Try to produce models that use simultaneously both modalities, because all the technology go from one line of research is speech synthesis, and other line of research is speech recognition, but they don't interchange information or even try to put all this stuff together. So I think that in cognitive speech processing, that can be a very interesting area of research. Well, I go on. This is also a simplified functional model, but a little more complex than the previous one. This was taken from Cernak work for cognitive speech coding. This is a dual stream model because here you have two streams. One stream is responsible for speech production, and the other stream is responsible for speech recognition and understanding. So here you have in yellow in the middle the auditory speech perception block or stage, and here you have with these arrows the dorsal stream and the ventral stream. The dorsal stream goes to the speech production stage, and the ventral stream goes to the speech recognition stage. Sorry, do you hear well me? Because there is a storm here, and it's very high background noise.
Yeah,
Can you
little
hear?
noise is there, but you're audible, sir.
Okay, wait a minute, please. Okay, now is this better? You hear me better? Hear me better?
Yes, sir.
Yes.
Okay, thank you. It's a very, very strong storm here. So this dual stream model is also a very, very simplified one because you only have there three main stages and some other details about, especially for the auditory perception, because this work is focused in auditory perception. But now for BCI, the focus has to be especially in speech production, also perception, because as I mentioned that they are really inseparable one from each other. Okay, this is a more complex dual stream model. In the upper part of the picture, you can see the functional blocks of the model. And in the bottom, you can see the anatomic correspondence with the different part of the brain. This is the left hemisphere, and this is the right hemisphere. As you can see, the auditory part or the auditory stream, it is located in both hemispheres. But the other stream is principally strongly left dominant, especially if the person is using his right arm, then this is left dominant. If the person uses the left hand, sometimes it's in the other hemisphere. But for one of those both streams, the main activities occur in one hemisphere only. So here you have with different colors the different parts of the brain here, also in the anatomic representation. So, for example, the dorsal pathway that it is in the upper part of the brain is in blue here and correspond to these blocks here, to the articulatory network and the sensory motor interface, because this is the sensory motor cortex in this part. The sensory motor cortex really goes to the other side also, but specifically for speech production, as I was already mentioned, is in one of the both hemispheres, generally at the left. So these represent the somatosensory, the sensory motor part of the process, the dorsal stream. And then in the ventral stream is associated with a lexical and conceptual representation of speech. That's the ventral pathway in pink color here. It's associated with syntactic, semantic, and something like that. Okay. Then here you have these blocks or stage in the ventral stream, especially the lexical interface and some combinatorial analysis network here. So during production or perception of speech, these regions activate in a sequentially or even simultaneously manner in order to produce or perceive the message. Okay. Well, this is a model with a little more detail. It's from this work of Timmers et al. 2011. So here you again have the functional diagram of the model and the corresponding anatomical structure and the location of the different activation at different stages. Here in this color bar, you have the different times after the stimulus or after the onset of the process. So these are the cognitive stage. You have here preverbal stage previous to the representations in terms of verbal and words. That's the preverbal. And then you have the verbal stage. The number here in every one of these boxes represents the approximate temporal encoding for each type of information. So here's the picture onset, and then the experiment is in this way. They show you a picture, and you have to produce the word, speech the word, they represent the picture you are seeing. For example, an apple, something like that, or more complex picture can be also. So as here remark, these boxes are only for facility in the for an easy representation, but really this is a continuous process. It's not like stage one and then the other and then the other, because really it's a continuous process. But in this other slide, I try to mention the main stage of the process. Again, the same picture. And for example, from 0 to 150 milliseconds, the visual system encodes the stimulus and activates the verbal concept. So you see the picture and begin to have an idea of what the picture represents. Then from 150 to approximately 225 milliseconds, lexical entries are selected. So here you select the appropriate word in order to represent the concept. This is in the medial temporal gyrus. In colors here are representing the same regions here. So you can follow a sequence, approximate sequence of activation of the different parts of the brain. Then from 250 to 350 milliseconds, syntactic encoding was done in the part of the inferior frontal gyrus. And then from 700 to 500 milliseconds, a phonological encoding occurs. For 500 to 600 milliseconds, message assembled and a speech plan sent to the premotor areas. This is like a pre-planning. You arrange all the parts of the message and with all the other phonological, syntactical, lexical rules, and you do some type of planning previous to the motor actions of the muscles. And then between 275 and 400, there is an online self-monitoring feedback loop between all the areas for production and some areas of perception. So these times are really very important. They are approximated times, but if you try to decode this type of information from for example, EEG signal, this type of time encoding can give you cues in order to where to look, at what time look the activation in different electrodes, for example. Okay. This is a particular model that includes also the cortical organization of the syntax analysis and the relation of this syntax analysis in the brain with the other parts of area of the brain as the sensory motor and conceptual semantic cortex or brain systems. So here, this is another model. This is a functional model here, and the corresponding anatomical representations. So again, the colors of the blocks correspond to some activation of some regions here. For example, articulography or articulatory regions or stage. And here you have the auditory phonological stage and the corresponding part of the brain and the auditory cortex. But here you also have the syntactic information appears in two parts. One is in the dorsal stream, and the other is in the dorsal, or this part of the brain, and the other in the ventral stream. In this zone. So this is a particular conceptual or functional mapping or model that includes a particular detail of syntax analysis, because here in the other model, syntax is all in one stage. So if you look in the literature, you really find many of these type of models. I tried here to put the ones I think that are more interesting to review, but really are plenty of this type of models, and it's difficult for researchers to agree in an unified model. But I think that every model has put the main focus in one part of the process, okay? Well, an important part of the process of production, as you see, is the motor aspects, the somatosensory and sensory motor part of the process. So here you have in both hemispheres, you have the in blue, like blue here, and here the somatosensory cortex, and in this color, something like red, something like that, you have the motor cortex. And this is a really somatosensory topic map. This is what is called the Penfield homunculus that shows the organization of the primary motor cortex. Every part of the body is represented here, in the motor or in the somatosensory cortex. The motor is associated to muscles or movements, and the somatosensory to the different sensations at the level, for example, of the skin and the sensory parts of the organs. So as you can see, this part of the cortex is associated to some of the organs associated with the production of speech. So there is really a map, and sometimes some parts of the cortex are responsible to move, for example, one particular organ. This was studied in the first experiment, um, stimulating different parts of the cortex and producing different movements in different parts of the body. That's a very, very basic experiment with animals and even with humans. So this is the main picture of what we expected to have activations in which part of the motor cortex or the somatosensory cortex. As I already mentioned, for speech production, this is a strongly lateralized process, especially with activity in the left hemisphere. But it isn't all the picture, because for a spoken language, a voluntary intentional takeover of the respiratory system, including the larynx and oral muscle, is also required. And such voluntary movements are under the control of primary and supplementary motor areas. And also the cerebellum, as we remember, we saw in one of the last slides. So with this type of image, you get an idea of which part of the cortex are responsible for each muscle activation. Okay, and here you have a study with I think that this is ECOG register over this particular part of the motor cortex and the Broca area here. And this study shows the somatotopic organization in the ventral stem or the ventral sensory motor cortex. Electrodes over ventral sensory motor cortex here are colored based on their distance from the Sylvian fissure, that is a particular anatomical structure in the brain that separates different regions. So here, a close-up view to this part, you can view in the graph. Different parts are there that are important in producing this type of sounds. And then here in this graph, you can see in these four diagrams, in one of the axis, you have the distance from one part of the brain, and in the other, the distance from another part. So you can see how, as the lips are activated, or the tongue or the larynx, several patterns appear there. And you contract a complex activity, motor activity here for the different parts of the phonatory system. So with this type of analysis, you can get more detail about how every electrode is activated by every stage of the production of one phoneme, for example, or one word. Okay? Well, and this picture shows a recent study from the group of Gallant. Gallant is a neuroscientist, very important in this field. So this is a really work where many researchers collaborate. It's a very big study. In this study, they try to look where the semantic information appears projected in the brain after the people or the subjects hear to, I think, something like 2 hours of a speech from a radio. So each one of the speech are segmented in the different words, and then a study was done in order to register which part of the brain has a high activity for each word. So this is like a semantic map of the brain. It's a very interesting project. You have some videos that you can see here explaining all the details of this study. And you also have a brain model that you can explore in more detail. It's very interesting because you have a three-dimensional representation of the brain, and then you can try to look for some particular words. And then the colors of the word are associated to some broad meaning. For example, social activities related words are in one color. For example, red here. Red words are associated mostly with social component. Green words are mostly associated with visual and tactile concepts. For example, if you think in a word that implies some direction, for example, up, down, left, right, that are spatial concepts, then a particular part of the brain activates related with the part of the analysis of visual and space, for example. And then it's really, if you go through all the map, you can find very interesting things. For example, I found the word Jesus and other words there like God and murder, miracle, something like that. You have there words that are related but by their meanings and in the specific part of the brain. So this really this study surprised the researcher because they expected that this semantic map appears only in a small part of the brain, but not in the whole brain. So this is another evidence that really all the processing that the brain is doing is completely interconnected. And especially for semantic content, you have this broad map over all the brain in both hemispheres, okay? If you have some time, I invite you to discover and look for the different words there. Okay. So what about other structures here? Because it seems that all is about the cortex, really. Because the cortex, you know, is principally the gray matter that are the body neurons. And that's the reason for the color, the gray matter. But which about what happens inside the brain, far from the cortex? The cortex, you know, really are only 5 to 6 layers of neurons. They are really the cortex. It is not so deep as we think, because there is 5 or 6 layers. But beyond the cortex, you have also all the axons of the neurons. That they are really the cables that connect all the areas in the cortex. This is really a circuit with connections for one part to the other. For example, the connection between the Broca area and the Wernicke area is there. And all we talk about the different streams can be detected and in this type of cables, we can say, in a simplistic way. So there is a particular type of study that is called a diffusion spectrum imaging that permits to represent this type of connections. This is what it called the connectome. The connectome is the representation of the different connection between the different parts of the brain. So also in this web page, you can see some of these pictures and also some 3D representations that you can also play with and see the different structures in this type of connectome. Okay? So, to summarize all we have seen, we can say that we have different types of neural speech decoding, and I use here some of the structure and words used by Rabbani in this work. First, you have, of course, the auditory decoding information, the auditory decoding dimension, you can say. You have the articulatory speech decoding information or dimension. You have the phonological decoding also. You have the semantic decoding. You have the syntactic decoding, always from neural signals. Visual decoding and also spatial decoding are the different dimensions you have to use in order to analyze the whole process of speech production and speech perception. And as we shall see, you have different forms of extract information related with each one of these different levels of information encoding in the different speech brain-related signals. Okay? A special remark, a special comment I have to do for the spatial level or spatial dimension. Because as we already mentioned, we have 2 years. So our auditory system is capable of detecting the direction and the location of a particular sound of source. So this is important also to differentiate the different paradigms. Because, for example, if you hear an external voice, you have an excitation, activation of the auditory cortex. But also in some parts of the brain that are responsible of spatial representation. And in this way, in this part, the information corresponds to a voice that is outside your head. But in inner and imaginary speech, then you hear your own voice, but inside your brain. So some studies, recent studies, show that here are also findings of important information related to imagine and inner speech. Okay? So this can appears to a non-important area for this type of paradigm. But recent study shows that really there is important information there. Okay. So the idea with this, all these dimensions, or cues for decoding speech from brain signals are important in order to extract the information necessary to control some device, for example, or even speech recognition from this type of brain signal. Okay. Well, any questions for this part of the talk? I think that is a lot of information, but it's really a complex phenomenon. And different authors have different models also. Okay. No questions? I can go on.
Yes, please.
Okay, thank you for the feedback. Okay, then now we go again to brain-computer interface. You remember here the block diagram we saw in one of the lectures with all these stages or blocks for the classical BCI. So the idea here is to focus our attention in the paradigm. The paradigm is especially the signal that you will use in order to control the particular device with the interface. So every paradigm has different signals that use in order to communicate with the device or the computer. Okay. So here you register as already saw the different signals with different acquisition systems or equipment. And then in this stage, you try to convert the information here to a particular command for the application. Okay, but in the middle, this is a problem of signal processing and classification. Okay, let's review the principal paradigms. As I mentioned, they are associated with mental phenomena and the strategy used to modulate brain activity, in particular brain activity, what I call the control signal. So you have what is called the slow cortical potentials, or ECP, the steady state visual evoked potential, SSVAP, or even relate potential, the P300 that we see an example in one of the previous lectures. The motor imagery, or even related the synchronization paradigm, and of course the speech-related paradigms like imagine speech, inner speech, etc. So in what follows, we try to review the principal aspects of every one of these paradigms. Let's begin with the slow cortical potentials. I used for these slides this review from 2012, and then I adapt for the new paradigms in this last slides. So slow cortical potentials are a slow voltage shift in the EEG that lasts a second, from 1 second to several seconds, below 1 hertz, associated with change in cortical activity level. Negative slow cortical potentials correlate with increased neuronal activities, while positive slow cortical potential coincide with a decrease in the activity in individual cells. This is the phenomenon. So here you can see the different registers. Here you have in red the part of the activation where the neuronal activity increase, but this potential decrease in amplitude. And in the other side in blue, you have the opposite. The decrease in activity coincides with an increase in this type of potentials. Okay. Well, the idea is that you can self-regulate this type of potential if you specifically train for this task in order to use this potential to control external devices. You can, by biofeedback experiments, you can train in order to use this potential in a voluntary way. Okay. But the success in training depends on number of factors. Not all the subjects were easily trained in the same way. It can be used to move, for example, a cursor in a screen and select the target presented on that screen, because with a very simple movements to up or down or left or right, you can move the cursor to select in the screen several actions. That's the main use of this approach. Oh. Question? Okay. Well, another type of control signals are the visual evoked potentials. The phenomenon is in this way. When you see some light, for example, appears some brain activity in the visual cortex. Brain activities modulation that occurs in the visual cortex appear after you receive this type of visual stimulus. So also you can modulate this type of stimulus. The amplitude of these visual evoked potentials increase as the stimulus is moved closer to the visual central field. Okay. So here you have again fMRI of the brain superimposed with some type of functional study of the back part of the brain. Okay, that is the visual cortex there. So particular modulations occurs in this part that you can use in order to control some device. Well, steady state visual evoked potentials occur when visual stimulation frequency is higher than 6 Hz. In the experiments, you can use stroboscopic light or blinking. This allows users to select a target by means of an eye gaze. You can direct your eyes to a particular part of the screen, for example, of the screen, and then you can control a speller or something like that. Okay, something like you see here. This is the type of spellers that used with these visual evoked potential paradigms. Here the screens or the light change periodically in illumination. So to produce this frequency higher than 6 Hz in order to produce the potential, because if you use frequency below 6 Hz, these potentials don't appear. Okay. Well, here are some animation, but for question of time I go on. Okay. Well, P300, we review this paradigm in the, I think, in second day. P300 are positive peaks in EEG due to an infrequent auditory, visually, or somatosensory stimuli. For example, you see a particular character you are paying attention, and then this type of potential automatically appear there. This is not intentional. The intentional part is you have to pay attention to a particular character, but the other part of the phenomena is completely involuntary. Okay. So these are endogenic response that are elicited about 300 milliseconds after attending this type of odd-vowel stimulus among several frequent stimulus. The problem here is that the performance of this type of controls systems or signals may be reduced because the user gets used to the infrequent stimulus. If you use this for a long time, performance can be reduced. And the important thing also is it don't require any training. Every subject, since the first time you put it there and give the instruction, and it can do the task. Okay. So here is the difference between the baseline registers, non-target, and the target one with the P300. Okay. Of course, in this picture is oversimplified because, as we will see, this is really an average of many of these type of evoked-related potentials. So as we saw, BCI comprises a matrix of symbols or commands. Rows, columns are flashed at random while the EEG is monitored. And user gaze at desired symbol and counts how many times row column containing the desired choice flashes. The count it doesn't matter if you count or do anything else. But the idea with this is that to maintain the attention in one particular channel. Okay. So P300 is elicited only when the desired row or column flashes. This is a classic Dawkins speller that we also review in the last lectures. But one problem with this type of potential is the very low signal-to-noise ratio. That's the reason for that single trial P300 is a very difficult task. Really, for getting higher signal-to-noise ratio, rows and columns must be flashed several times for each choice. Okay, so you have to see the flash for your character many times and average the response over all this in order to get better detection performance of the potential. Okay. Okay. But the problem with this is that repetitions, of course, decrease the number of choices per minute. For example, 15 repetitions, you have only one chart per minute. Now, this is very slow. So here in this image, you have what it looks the target in gray, so the non-target in gray and the target in blue. As you see here from one of the EEG channels, they are both very similar. So it's very difficult to detect where the P300 appears really. This is a 5 trials average, 15 trials average, 500 trials average, and 2,500 trials average. And here you see the P300 more clearer, okay? I think that these are inverted, the labels. Okay. Well, here is the same, but for the different channels. This is a bidimensional representation because here you have different channels in the row and time in this horizontal axis. Okay. And this is non-target, and this is target. Here you can clearly see the positive wave in most of the channels at 300 milliseconds. Okay. But here is the same, but for single trial. This is an average, I think, 500, something like that, trials. This is only single trial. Again, it is very difficult to find here where is the information in order to detect the P300, okay? Well, this is a graph that represents the bit rate here for the transmission between this BCI and the computer, and the number of trials. So this is really an ideal curve for the degradation in performance when you augment the number of trials. But really, this was done with a classificator. You use a classification stage in order to detect in a binary classification problem if it is target or non-target in a particular moment or particular part of the EEG. But really, when you train the classificators or the classification stage, the result is not perfect. So really, you got something like that. Because with less number of trials, then the error is higher. So the bit rate it is affected because you have to, for example, delete a character if it is online, or suppress if the confidence of the classifier it is not so good, you have to do it again. Okay. So this is one of the problems. Most of the research of the last years focus in trying to solve the problem, but with only one trial. This is a very difficult problem, as you can see. Okay. Any question until this part? Okay.
No, sir, it was clear. Yes.
Okay, thank you very much. So the other paradigm is the sensory motor rings. This is the phenomena really. We try to measure in some way. Sensory motor waves, mu and beta, are oscillations in brain activity over the motor cortex, localizing these two frequency bands. The mu band between 7 and 13 hertz, and the beta band between 13 and 30 hertz. Okay. In this picture, you also see the MRI and the corresponding activation of the mu waves that can be detected from both sides. Okay. This is the homunculus. Again, the homunculus map here, and you can modulate in some way this type of sensory motor rhythms when you are doing some particular motor task. Okay, for example, you can move or imagine to move the right hand, or that appears in the left side, of course, because this is all crossed. One movements in one side representing this cerebral hemisphere of the other side. And here, for example, is the activation of the motor cortex when you move or imagine to move the left hand. And similar to the leg or foot, following this type of mapping, okay? So the amplitude of these two rings in these frequencies varies when the cerebral activity is related to any motor task. Similar modulation patterns are produced as a result of mental rehearsal or imagination of a motor act without any overt motor output, okay? Something like motor imagining. Users can learn to generate this modulation voluntarily in the sensory motor rings, using this imagination of the movements. Training should emphasize kinesthetic experience instead of visual representation of actions. For example, you try to imagine how you feel when you close your hand, but trying not to imagine the visual animation of your hand when you close or open, okay? Visually or auditory feedback can be provided according to the success of the result, so you can repeat the task if you fail in produce good results, okay? Well, can endure two kinds of amplitude modulation, known as event-related synchronization and event-related synchronization. There are two types of events that you have to detect in the EEG, for example. ERD involves an amplitude suppression of the ring, and ERS implies an amplitude enhancement. So here in this picture, you see how these two potentials appear in a specific frequency. This is the gamma frequency here, ERS, and here is the post-movement beta band for the ERS also, and this is the mu band for the ERD. So there are particular patterns for this type of activations. So you have to detect these waveforms in order to know when the person is imagining a particular movement. And here you have the same representation, but at the level of the EEG in the different channels, okay? Well, this is the classical paradigm, but in the last years, as you know, this is one of the issues we are discussing in this course. Appears a new paradigm, or I think some new paradigms related with the speech activity. Okay, subjects have to imagine themselves talking without moving muscles and producing sounds. That's the idea. This is a more natural way for the user to communicate than the previous one, because as you surely know, some of the other paradigms are really non-natural for the subject. Sometimes even you have to train the subject in order to a useful application of the paradigm. Okay. It requires less time for training for the subject. Really, sometimes you don't need any training for this type of speech-related paradigms. But it's a complex classification problem with several challenges that we will review, but can potentially improve data transmission rate. You see in the other paradigms that you can only communicate at the bit rate very low, something like 1, 2, 3 characters per minute. That's a very low rate for communication with the imaginary people in a wheelchair, that, for example, try to give orders to the wheelchair in order to move through the house. And suppose you are close to stairs, and then you have to give a fast command or fast response, I think, in order to not to go through the stairs, something like that. So for real-time application of these brain computer interfaces, it is very important, this type of speed of the communication, okay? And of course, these are the most recently appeared paradigm. In this table, the main characteristics of each one of these control signals appear. So here we have slow cortical potential, so visual potential, 300, motor imagery, and speech related. Okay. Here you have the physiological phenomena as we described, the number of choice you have, the necessity or need of training, and the information transfer rate. As you can see, for example, SCP, we in general have a low number of choices available, 2, 4. It is very difficult to have more than this in every one of the stages of the control. With BEP, you can have much more than that. Then for 300 also you can have many classes, the different characters. Although really you solve a binary classification problem, okay? For the motor imagery also you have low quantity of different alternatives that you can choose with the interface. And in most of the works of speech-related paradigms, you have a medium quantity, between 2 to 8. In general, are vowels you can use or words associated with directions or something like that. In all the cases are small vocabularies, okay? So some of them require training, some of them no. But speech-related, some of them really need a very, very small time for training. For example, the training consists in hear the instructions and try to apply to the task. It's really very, very easy, okay? And of course, here are the different velocities of rate of information transfer. So as you can see, they're all slow connections. We think that if you can get a good performance, here you have same rate as the rate of normal speech recognition or communication, okay? And in a more natural way than the other paradigms. Well, in what follows, I will review the speech-related brain-computer interface and the corresponding paradigm. So let us review what we saw of the speaking modes in the previous lecture. As you remember, you have speaking modes with acoustic output and speaking modes without acoustic output. Speaking modes with acoustic output called overt speech. You have here the ones with glottal activity, modal or whisper speech, and the ones corresponding with the level of effort in order to produce a speech that can be divided in normal, shouted, or mumbled speech, okay? And in the case of without the speaking modes without acoustic output, you have they called a covert speech. This is overt speech, and these are covert speech. So inside this type, you have silent speech, imaginary speech, and inner speech that we will now try to review the principal characteristic, okay? And here for illustration, you have a representation of the overt versus covert speech brain activation from this work. As you can see that the principal common regions of activation are in the auditory, and this is the ventral stream, auditory and ventral stream, and near the motor cortex and sensory motor cortex. Okay. Well, inside covert speech, that is the covert speech modalities are the ones we are interested for control brain-computer interface. Okay, so we have a silent speech where speakers are instructed to move their articulators as if producing normal modal speech, but to suppress the airstream from the pulmons, so no sound is emitted. Okay. Imaginary speech is similar to silent speech, except movements of the articulators are also suppressed. An inner speech, sorry, inner speech, really there are a lot of different denominations for this phenomenon, like covert self-talk, verbal thinking, inner voice, or inner dialogue. Okay, but we define following this author and others, we define inner speech as an internalized process in which one thinks in pure meanings, generally associated to an auditory imagination of our own voice. Okay, we will see in more detail every one of these classes or modalities of speaking modes. Okay, for silent speech mode, so the main characteristics are that silent speech production can be measured by monitoring articulatory movements using motion capture devices, imaging techniques, or by measuring the activity of muscles, as we saw with EMG. Okay. For that reason, and strictly speaking, it is not a BCI paradigm, because for BCI you can't use any muscle. Okay. Although this is really a particular mode of speaking, but in some authors use this as a paradigm also. Okay. In addition, some also propose a similar mode called intended speech, where the participant that have some type of problem with the capability to emit sound, they ask them to perform speech. So they try, but they couldn't. So, okay, but they produce some activation of the muscle in some way, and you can register that activation. This is it called intended speech. Okay. Let's review the imaginary speech paradigm. The main characteristics are that it is similar to the silent speech, but without any articulatory movement. It's such like a motor imagery of speaking. Okay. The participant must feel as she or he is producing speech, first person experience, mainly focusing on the different articulatory gestures. Since it produced without any articulatory movement, requires observation at the neural level only, to have any other signals to look for. And this paradigm was widely explored using ENG, MAG, and ECOG. Okay. Generally, speech materials we are carefully selected as they have the most different articulation process. Okay, for example, you have to plan which words are really different from the point of view of articulation in order to get better results from this type of control signal. Okay. Well, in the inner speech paradigm, uh, well, inner speech is a mental phenomenon very studied by psychology in the past. So we have many descriptions, even though in some type of illness, uh, like dementia, appear some of these internal voices, not your own voice, and they are associated to some type of hallucinations. Okay. So in contrast to imaging and styling speech, no phonological properties and turn-taking qualities of an external dialogue retain. For example, in a real dialogue with acoustic signals, then you have some cues in order to know when the other person take the turn in order to talk. Okay, this type of cues are not present in inner speech, as the researchers find. So this inner speech is even more difficult to investigate than imagined speech. Okay. Compared to the brain signals in the motor cortex, motor system, language processing appears to be more complex and involves neural networks of distinct cortical areas, as we saw previously, engaged in phonological or semantic analysis and speech production and other processes. So this is really a more difficult task than imagined speech that is focused principally in motor aspects of the phonation. Okay, different studies use different techniques like EEG, COG, fMRI, or even PET scans. Okay. Well, which are the main difference between these two paradigms, inner speech versus imagined speech? The key point here to distinguish between both speech-related paradigms is looking for distraction given to the subject during the experimental protocol. For example, for imagined speech, the particular instruction can be imagine mouth opening and imagine vocalization, for example. This is one of the instruction gave in the Sala work, for example, for imagined speech. An example for inner speech is the one we used in our recording of our inner speech database that we used in the tutorial session yesterday. For inner speech, for example, you can tell, imagine your own voice as if you are giving a direct order to the computer. And then each participant was explicitly asked not to focus on articulation aspects. Okay. So the key point here is which are the instructions given to the subject. The type of stimulus presented to the subject is also important. For example, you can give an image or a sound, and this will have some condition over the type of response elicited with these paradigms. Okay. And at this point, I suggest you to see this short video where this researcher, Rebecca Kleinberger, talk about why you don't like the sound of your own voice. Because she said that we really have three voices. The external voice, the voice that the people apart from you hears, the voice you hear, acoustic here from your own production, but convolved and filtered because of the bone transmission, not only acoustic. So your own voice sounds different for you than from the other person. So you have something like two different voices with different characteristics. And the third voice is precisely the inner voice, the voice that you hear inside your head, okay, with no acoustic corresponding signal, okay. Well, in the end of this talk, I will try to have a fast review of the different BCI types, okay. A BCI can be classified as exogenous and endogenous according to the nature of the signals used as input. Also, they can be synchronous or asynchronous according to the input data processing modality. And also you have active, reactive, and passive BCIs according to the role of the user in the paradigm, okay? So exogenous BCI use the neuron activity elicited in the brain by an external stimulus, such as visual evoked potential or auditory evoked potential. So in exogenous BCI, you need an external stimulus in order to work, okay? In the other way, endogenous BCI is based on self-regulation of brain rhythm, like imagery alternatives, motor imagery, for example, and potentials without external stimulus. The stimulus is, you can say, internal. That's you use the word endogenous, okay? And here is a table where you have the different approaches and the different paradigms that are in the different classification, okay? These are the graph where you can see the different modalities. The evoked or endogenous, exogenous, sorry, and the spontaneous or endogenous, okay? And it's similar to the last table, okay? Well, another modality or type of BCI are the synchronous BCI. In this case, you analyze brain signals during predefined time windows, and any brain signal outside the predefined window is ignored. So this is synchronous. The person has to make the task in a particular time window. In asynchronous BCI, continuous analysis of brain signals, no matter when the user acts, is doing. Okay, you continually register all the signals and try to look for some type of control signal there. So the synchronous approach is most simpler than the asynchronous one. But the synchronous one is really more natural. So at the expense of this naturalness, it is more complicated to design and to get a good result from asynchronous BCI. Okay. And then, according to the role of the users, you have active BCI, where in this type of BCI, it's output from brain activity, which is directly consciously controlled by the user. So the user controls directly the control system, the control signal, sorry, independent from an external event. Okay. In the reactive BCI, It derives its output from brain activity arising in reaction to external stimulation, which is indirectly modulated by the user. This is some type of semi-consciously controlled signal, okay? And at last, you have passive BCI. In this case, the outputs are from arbitrary brain activity without the purpose of voluntary control of the subject. So the subject here is doing nothing, or not voluntary or consciously in control here over the BCI. Okay. Well, I think that this is all the material for this lecture. So I hear your questions at this point.
Sir, any commercial products are available for BCI currently?
Commercial, sorry?
Commercial products based on BCI?
Software, you mean?
No, means are there any products available which are ready to use by the users based on BCI principles? Commercially
Okay.
available products.
Yes, really nowadays, the main these paradigms I have just showed you are very interesting for research purposes, but for practical use, for everyday use, they have several problems. One of the problems is the one we mentioned about the need for periodical calibration and the difference between the offline train of the classifiers, for example, and the online function of all these paradigms. Another problem is the cost of the equipment, because low-cost equipment in general have lowest signal-to-noise ratio, so the performance is worse than the other approach with more expensive equipment. That are only some of the drawbacks of applying this type of techniques for everyday use in real world situation, because you have some I think devices you can buy for really under $1,000, like Emotic or something like that, that you can use for playing or doing some type of activities that are commercial devices. So you can buy them, you can use. The manufacturer sells you also a different type of software, so you can control your computer or play some game or something like that.
Yeah, okay, thank you, sir.
Okay. And this is a good point, because it's a challenge to try to get these techniques more close to the people they need them. Okay. But another problem is that most of for example, the database and the studies are with a person without disabilities. But really, the person that needs this type of interface are persons with disabilities, with some type of disabilities. But in that case, the signals, the registry of the signals and the signals itself are very, very degraded, because sometimes there are some brain injuries there that affect the registering and even the behavior from the person. So that's the most difficult situation, and very little research is done there.
Okay, sir, thank you.
Another question? Okay. If there is no more questions, I think that we can proceed to the tutorial.
Okay, sir. I will request Ayush to go ahead with the tutorial.
Yeah.
Let me restart the recording.
Okay. So good evening, everyone. So today we will discuss on the imagine speech classification. So, imagine speech brain computing interface. So the objective of this tutorial will be to understand the basics of imagine speech in brain computing interface paradigm. Working with the real imagine speech database, we will be doing that today. We will be trying to replicate one of the research work that Professor Ruffin has already mentioned in his talk. And we will be using wavelet transform as the feature to extract features from EEG signal and then apply machine learning algorithms to classify whether the speech is imagined speech or pronounced speech. And further, we will be also doing the classification based on the commands and the vowels that the list is imagining. Now let's go and see how the database is been collected and what's the distribution of the database. So imagine speech database contains EEG records of 15 volunteers, out of which they have spoken imagined 5 vowels and 6 commands. So those are 7, like the population is 7 women and 8 men between the age of 24 and 28 years old. So they have been speaking this vowels, Spanish vowels A, E, I, O, U, and other 6 control commands. Basically, those are Spanish commands. So how the database is distributed. So these are the commands that I was saying: up, down, right, left, forward, backward. So these are in Spanish that they have imagined. So how the database is distributed is, like I will show you. I have already mailed you this imagine speech database. I hope you have downloaded that. So this is how the imagine speech database is distributed. We have 15 speakers, as I said, out of which 7 are women and 8 are men. And inside, if you go, you will get the audio.mat file and the eeg.mat file. We will be working on this one currently. Okay. Yeah. So imagine speech database, then like we have audio.mat and eeg.mat. So the so there are 6 channels in through which the 6 electrode channels through which data has been collected: F1, F3, F4, C3, C4, P3, P4. This has already been discussed in the lectures. So like you can see here how it's placed here. So let me show you how it's looks like here. Yeah.
Sir, can you please zoom it?
Yeah, sure. Now it's okay, right?
Yes, sir. Right.
Yes. So we will import the data. It's the .mat file, the eeg.mat. We will just import it using import data command in MATLAB, and let's see how it looks like. So it's 24579 samples has been collected for this speaker. So if you see, so there are, from EEG data we have 24576 samples, and there are 3 labels here for which that will help us to do the classification. So You see the this thing. So we have three labels, three modal. Like first one is the modality imagined on pronounced speech. So this is what label this label tells us. The third last label, it will be either 1 or 2. So it's either 1 or 2, right? So this will tell us whether it is the imagined speech. This is the label for imagined speech or the pronounced speech. The second last label will tell us whether it's vowel or command. For A, it is 1, E, it is 2, and so on. Up to 9 labels are there. So you can see different labels, which the, 11 labels. Sorry. Yeah. Here there's a typo, like 6, 7, 8, 9, 10, 11. 6 commands and 5 vowels. So those things are there. So 11 labels are there, and the last one is either it's blink or no blink. This artifacts, these things. So in this way, how the EEG dataset is distributed, and also it's collected at the sample rate of 1024. Now, so as I said you that there are 6 channels. So the how the database is aggregated is like 0 to 4096 is from channel F3, then 4097 to 8192 is from channel F4, and similarly if you see this, like, so once 4096 is basically when sample rate is 1024, it's 4 second, right? So that is what they are here also mentioned, 4 second at 1024 samples per second. So we have for every channel 4096 samples. So similarly we have 6 channels, so we have 24576 samples. So these are aggregate in single array. Like you can see, these are aggregated on single array. So we have to separate the data for every channel. So that we have to do. We have in the code that I have already sent. There is a function written channel, like it will distribute all the channels that is available in this EEG. So let's see how it distributes it. Yeah, so the first channel F3 is from first sample to the sampling period, right? 4 into sampling rate. That is 4 into 1024. Similarly, F4, FC3, and all the things are segregated, and finally the 3 labels at the end. That will help us to do classification.
Ayush?
Yes, sir. Yes, sir.
Yeah, that columns in the mat file, no? Each
Yes, sir.
column has 6 channels, or each column?
Each column has 6 channels, sir.
So the other, so it is a complete data, because what are the other columns representing? So because there are so many columns, right?
Yes, sir. 1, 2, up to, yes, sir. There are so many columns, right? So every like it's samples. Like we have time. In time we have seconds, right?
Yeah.
We can represent it in samples also. So there are 6 channels that have been concatenated to make an array. So that is what every up to end what we have is 24576. So if you divide it by 6, you will get 40 some that 4 into 1024, right?
What I meant to ask was like all these columns represents it consists of all the vowels or all the data what we are going to
Everything.
build the model.
Everything. Yes, sir. Yes, sir.
Okay. It is okay. It's a pool of all the utterances.
Yeah.
Right?
If you see the labels here, if you see this label, so this column, this row belongs to an imagined speech which has been pronounced as this thing. which has been pronounced as,
Oh,
I don't
okay,
know the
okay.
Spanish pronunciation of
Oh,
this,
okay, okay, fine, fine, fine. Yeah.
and that is also a blink. So
Yes, yes, yes.
oh,
Okay.
yeah.
Got it. Okay.
Ayush,
Yes,
yeah, what does this 688 correspond to?
688. So I think I'm not sure very much, but I think these are that many imaginations the speaker has made. Yeah. So we have separate. We will separate for every row here all the imaginations the speaker has made, and if you plot it, it will look something like this. So when all the channels are concatenated, and this is for F3, F4, C3, C4, and then other two, I guess it's P3, P4. So this way all the channels have been segregated. You can see it's 24 here, and 24 by 6 channels are there, to 4 for every channel we have it. 4 seconds of data for every channel we have. So we segregated it there. Yeah. Now let's go to the doc again. So as we have already seen in the MATLAB that if these have been concatenated, and last one is the label. So here are the trials, like as you asked, and here is the time. Now coming, let's come to the feature extraction stage. Like we just can't process the raw EEG signal. We have to extract the relevant features, because EEG might have various redundant features also. So we will extract that. Let's come to the feature extraction stage. So we have, how many speakers do we have? We have already seen we have 15 speakers. So we will extract the data feature for that. So here just I have pasted the base path, and you see here, we'll run it. So we have 15 folders for which we have to do the feature extraction. And one more thing that they have, the document has mentioned is, we have to load the database and select the subject or trials we want to use. Separate the different channels that we have already done. Now we will downsample the EEG. For this is done just for faster processing. Then the main feature that will be used is discrete wavelet transform. Like MATLAB already has a function called, I'll show you that function name. Function called wavedeck that does the wavelet decomposition, wavelet transform that you call. It does it for you.
Excuse me,
Yes.
sir. Yesterday we had seen that some pre-processing was also done. So here pre-processing is not done.
If feature extraction, I think that is by pre-processing here only I have shown. Like pre-processing is basically, there are in single channel we have concatenated, like in single array we have concatenated 6 channels. So we have to segregate all the channels and the labels. That is what we call it as pre-processing here.
Yeah, that is fine. But yesterday that 50 hertz notch filter was introduced, and
Okay. No, that is not done here. I guess the data set is clean only.
I think that in this case, you don't have the raw data. This is the pre-processed data.
Okay.
okay, sir. Thank you.
Okay, sir. Thank you, sir.
Sir, this data can be, for the non-imagine, other than this classification, we can use it for vowel classification also.
Can you repeat? Sorry.
Yeah,
Yes,
here
yes,
we are
yes,
going
sir.
to go for a binary classification, no? Whether imagine speech or non-imagine speech, right? So instead of that, since the database is a little bit complete, so we can go for the vowel classification also, like whatever the vowels are there.
Do you mean in the tutorial, or
Yeah, I mean, general I'm asking with respect to this database.
okay. You can use the database for many different tasks.
Oh, okay.
The basic is the classification between modalities,
Yeah, yeah.
but you can also do the classification inside each modality and each material between vowels or between words.
Oh,
And also in some words, I see that they used it because this database is really very used by the community. Is I found some 12 different works using this database. For example, one of them used it for multimodal biometric system. So they can use the speech and simultaneous recording of EEG in order to classify the identity of each subject, something like speaker identification. So the data is there and you can use it in several ways.
Okay, okay, sir. Thank you, sir.
So, yes. So we have done this feature extract. We have extracted this the features using the wavelet transform, and we got the coefficients from there, like we call it, and we aggregate all. We have like aggregated from all the trials into single array, and we have also aggregated all the labels and also the labels of all the commands, and using just like we are just concatenating over the for loop. Now we will load it into save it into a .mat file so that we can do it. We can now till this step we had completed our feature extraction part. Now we will go for the classification part. So we have loaded all the data, the labels, the command data, all the 11 labels that we had. We have stored it into a mat file. Now let's go for classification part. So this code has also been shared with you. So we will be using sklearn library for doing this classification. So this scipy.io will just load the. Hello. Yes, yes.
Yeah, I have a question. So here for this problem, why do we consider only 6 channels and specific 6 channels?
Professor Rufina, can you clarify about this?
Can you repeat the question? I didn't hear.
Yes, so for this particular problem, why do we consider specific 6 channels?
Yes, really, we have only access to this low quantity of channel amplifier at this time. So that's the only reason. The equipment has good amplifier, but very few channels because it's a little old equipment. But as we can see tomorrow, some of the papers of other authors have very good results with this small amount of channels. The possibility of use low cost equipment is very interesting also. Okay.
Or is this because electrodes are placed on the temporal lobes?
Yes, you talk about the positions of the electrodes, not only the quantity.
Yes, sir.
Okay. Yes. We put the electrodes over both sides and over the temporal lobe, because near that you have motor cortex and also near auditory cortex.
Okay.
Some of the results show really more discriminate information on the left side of the electrodes, or the electrode from the left side. Some studies of this type were also conducted, but after the recording of the database. Okay?
Yes, sir. Yes, sir. Okay.
Thank you.
Okay. Thank you.
So we have loaded the database here, and from that database we have got the data. Now what we will do is we'll split into train and test. Just in sklearn we have this facility. We can just use this command and we can just split the data into train and test. Now for we got xtrain, xtest, ytrain, ytest. Now here in this we are doing two classification. The goal is to classify between imagined speech and pronounced speech. So we have used, I've used decision tree classifier. You can use SVM or random forest or any two classifier as you want. Like here, I have used the decision tree classifier from the sklearn library. So what we have to do is first import the decision tree classifier and then give the input data and the true output that you want to predict. Here this decision tree underscore model is the variable that will contain your model and all the parameters of that. Now this is all about the training part. So this sklearn library is a very good library. You can see, like, using just a simple one command, you have completed the training process. You just have to give your input and the output. So similarly, there are many other classifiers that are there in sklearn. Like SVM is also a simple one line command that you can use. Now for predicting, you just have to give the test that you want to predict, x underscore test that we have segregated above. It will give the predictions in labels, either 1 or 2. Okay. Now here I've printed the confusion matrix also. The data, if you see, it's very sparse. Like the imagined speech data is more than the pronounced speech data for this database. So the prediction for this true prediction for the imagined speech is 1792, and the true prediction for this one is like 19 for pronounced speech. If you see the accuracy, like this is a function that will compute your accuracy. If you see the accuracy for imagined speech and pronounced speech, it is giving around 77%. Like why like, since the data is more of imagined speech, even if the pronounced speech is getting classified wrong, it will it will give 1, and so because of that the accuracy has gone high. Like we need much more better algorithm for doing this classification. Now this is for two class classification. It's simple, like just you can see that just importing the decision tree cluster from sklearn library and fitting the data, you got the predictions. Similarly, you can do it for 5 class classification. I have done for that also. In 5 class classification, we are doing classification of all the vowels, A, E, I, O, U. So for that also separately, I have done this feature extraction. I will share these files also. We'll share the vowels files also. Like all the vowels are between 1 to 5. So all the labels that are between 1 to 5, that will be get stored in this vowel data, and I will store it in vowel data.mat. Further, all the labels that are less than 5, then the labels will be stored in vowel label, and that will be stored in vowel label.mat. So the same procedure as we have done for 2 class classification will be followed. Just load the data, vowel data.mat and vowel label.mat. Then you split it into training and testing set using train test split. Further, using the same decision tree classifier, you learn the model and do this fit. Here you can see if you see the accuracy, it's coming around 20%, still a chance level accuracy. But if you compare it with the paper that Professor Rufina has published, so there is also like around 19.3, and for random forest we are getting 23.68. But for decision tree, like we have applied decision tree, so we are getting around 20% accuracy. Like you can see a 20.07% accuracy of prediction.
Ayush, this is accuracy or the error rate?
No, sir, accuracy. Like just I have. If you see the
Out of
function
100.
here, I have just matched the labels. How much percent is the match
Okay.
between?
20% out of 100, 20.
Yes, yes, yes.
This is sorry. This is a slow value for accuracy, but this is upper than chance level.
Yeah, it's upper than chance level. If you see the chance level, it will be 20%. So in the paper that they have mentioned, it's like 23.68 for random forest.
This is also a very basic classification approach in the feature vector and also in the classifier. So these are only illustrative results in order to get some as a baseline. But if you work more carefully for in the feature stage or in the classifier stage, you can get even better results. Something like, I think that the best result with this data is about 65% of accuracy. That this is better than this.
Yes, sir. Is it using deep learning, sir?
Yes, some of them, yes.
Okay.
Yes. This is a very basic approach.
Yes, sir. Yes, sir.
Yeah.
Thank you, sir.
Now, that was for this 5-class classification. Further, sorry, it's 11 here. It's 11 class classification. Like I've taken all the 11 labels. I mean, all the 11 commands, A, E, I, O, U, and all the 6 commands that I have already shown in the second last table that was there. So similarly, all the data, like the data for this thing for EEG data was loaded in the mat variable, and the labels of the commands, that are 11 commands that was loaded here. And the same procedure again, it was applied, splitting the data set into train and test for the learning decision tree classifier. And here, if you see the accuracy, it is around 11.76. Still, it's like above the chance level performance. If you see 1 by 11, it's around 9, something around 9, and we are getting here greater than 9. It's 11.76%. So here we have 11 classes. So using classification and using decision tree classifier, we are getting 11.76. So yes, so that's till today the goal was to see the feature extraction stage, the basics wavelet transform that we have used, and the machine learning algorithms that we can apply to get the accuracy. In tomorrow's tutorial, we will see the deep learning approach and the further more enhanced features.
What is the motivation for wavelet based features? Why not others?
So like wavelet based features is like we make small clusters. Like it's advanced version of wavelet transform. You know already, like it's advanced version of this Fourier transform, right? We make a cluster and then we learn these things.
Yes, the idea is that it's something like a filter bank.
Okay.
Because you get the power in each one of the bands. You retain only one coefficient per band per channel. So you maintain a low dimensional feature vectors in order to make the classification.
Okay.
But it's also a very basic approach because you didn't take into account the dynamical aspects of this type of signals. You only have a frequential approach. Only frequency characteristics are there for each channel, and you try to put important information in the classical bands.
Okay, sir.
Okay.
That's good. Yeah. Thank you. Thank you, sir.
So that was for this for the demonstration for today's tutorial. So if anybody have any question, I'm ready to take them. Like I will share this document also, like you will get a better visualization because everything step by step has been written here. So I will share this tutorial and the like this code also, the other two classifications, 5 class classification code and this 11 class classification, and this 2 class I have already shared it. Further, yeah, that's it.
Ayush,
Yes, sir.
I think that whatever you shared, no, like
Yes,
the
sir.
database, I think it is asking for the permission.
Permission. Oh,
Yeah.
okay.
Yeah, so I think those who are accessing from the other than Gmail, no, I think it will ask it.
Okay, I will make it available for everyone in.
Yeah,
I will change the link permission.
Yes.
Okay.
Yes.
Thank you for letting me know, sir.
Yeah, thank you.
And Ayush, is this an open database? I mean, can anyone use for research purpose?
I don't know about that. Professor Rufina, is it?
Yeah,
open?
it is open, I think. Professor Rufina can.
Yes, this is an open access database. Everyone can use it.
Okay, and okay, yeah, okay.
Okay, so if there are no more questions, we will close for the day. We'll meet tomorrow at 2 p.m. again.
Thank you, sir.
Please remember to read carefully the paper was assigned to every one of you. So we can discuss in the last part of the session tomorrow.
Yeah, we
Yes,
have shared you the paper link. We have allotted three like that, and you can discuss and you can read that. Okay, thank you.
Thank you.
Thank you, sir.
Just a minute, like I'm sharing the attendance link. So you just fill this Google Doc, the feedback and the attendance. Yeah.
So, hello, Professor Rufina, are you there?
Yes, I am here.
Sir, tomorrow maybe Prasanna sir will not take session. No? So, will you start from the session at 2 or what will do?
Yes, we start at the established time. I take the time to in order to have more time to the lectures and also for the discussion. It is okay. I think that with the discussion and all the material we have to share tomorrow is good. That amount of time. And also after the tutorial, we have the examination.
Maybe what we can do, yeah. Yeah, so what we can do, maybe first we can complete your lecture, then we will do the tutorial. After that, you can go for discussions and exam. Or
okay, yes, we can do it in that way, no problem.
okay, we'll go. Yes. Okay, sir, fine.
Okay. So perhaps you can sing in
Thank you,
2
sir.
hours.
Yeah.
2 hours, the first 2 hours of lectures, and then the tutorial,
Yes.
and then the
After
discussion.
that,
another 2 hours.
1.5 hour or 1 hour. Yeah. Then followed by discussion and then exam. Yeah.
Okay. Thank you.
Yes. Okay, sir. Thank you. Thank you. Thank you very much.
Hello. Hello. Jagadbandhu. Hello.